Hey everyone, welcome to this exciting course on TypeScript. Get ready to elevate your coding skills as we dive deep into the world of TypeScript. You'll learn everything from managing complex data structures to implementing advanced type features. And we'll do all of this while working through some hands-on coding exercises, which, trust me, will really solidify your understanding. Plus, there's a treasure trove of resources available with a link to our GitHub repository in the description, so don't forget to check that out. And stick around until the end, where we've got an amazing final project waiting for you that will really test everything you've learned. So, are you ready? Let's get started! You want to get started with TypeScript? Fantastic! The big question is, how do you begin? Your journey into TypeScript can be both exciting and, challenging, but fear not. It's a lot like mastering a new instrument. Once you get those basics down, you'll find you can create something truly beautiful. So, let's dive right in and set the foundation for our TypeScript project. First off, we're going to make sure you have everything set up so you can code efficiently. All right, let's get started. Now, let's create a new directory for your TypeScript project. You can do this easily with the command mkdir my-TypeScript project. This command creates a new folder named my-TypeScript project in your current working directory. Now, this step is crucial. Why? Because it helps keep all your project files organized and separate from other projects, effectively setting the stage for your development work. All right, once the directory is created, you'll want to follow up with the command cd my-TypeScript project, which changes your terminal's current directory to this new project folder. Think of it as stepping onto the stage where all the subsequent actions, tasks, and code will play out within this neatly organized space. By establishing this structure early on, you're ensuring that your project remains manageable and that all resources are easily accessible as you dive into coding with TypeScript. Next, we will initialize our Node.js project to create a foundational package.json file. This file serves as the manifest for our project, outlining key information such as project dependencies and configurations. To generate this file quickly, we'll use the command npm init-y, where the -y flag automatically accepts the default settings, streamlining the setup process. Now that our project is initialized, let's see how we can install TypeScript as a development dependency. This is done using the command npm install-savedev TypeScript. By using the -savedev flag, we indicate that TypeScript is a tool we need only during development, and it won't be included in our production deployment. Think of it as packing your toolbox for a project. While essential for building, it's not something you take with you once the work is done. This sets us up to leverage TypeScript for added type safety and features in our application development.
Now that we have TypeScript installed, let's dive into how to set up its configuration file, tsconfig.json, to tailor TypeScript to our project needs. The command npx-tsc-init generates this configuration file. It's pretty neat because it allows us to specify various compiler options. For instance, we can set the target to ease next, which enables TypeScript to compile our code into the latest version of JavaScript. This ensures we can leverage modern JavaScript features, which is fantastic. Next up, we want to set the module to commons. This is crucial for Node.js applications since it dictates how modules will be handled. CommonJS is the module format used by Node.js. Additionally, we can enable strict mode. This is great because it helps us catch errors early and really enforces type safety throughout our code. Now when we set ES-module-interrupt to true, it allows those legacy CommonJS modules to work seamlessly with ES module syntax, which is such a relief. And finally, don't forget to enable skiplib-check. This option speeds up the compilation process by skipping type checks on declaration files. By configuring these properties, we're establishing a robust foundation for a TypeScript project that is both efficient and well-structured. Now let's dive into implementing a simple TypeScript snippet to give our project a solid start. In this example, we're going to declare a variable named greeting and explicitly annotate its type as string. Now, this type annotation is one of TypeScript's core features, which allows us to catch potential type-related errors during development rather than at runtime. This helps make our code more robust, which is always a good thing, right? So we assign the value hello TypeScript to this variable, demonstrating just how straightforward it is to set and manage types in TypeScript. Following that, we use console.log to output the value of greeting to the console. This is a great way to check that our TypeScript setup is functioning correctly, because we should see the message displayed when we run the compiled JavaScript. Essentially, this code snippet lays the groundwork for understanding how variables and types operate in TypeScript, while also providing immediate visual feedback once executed. By practicing this, you'll become familiar with basic TypeScript syntax and concepts that will serve as a foundation for more advanced topics down the road. Now that we've got some code written, let's dive into compiling it into JavaScript. First, we'll use the command npx_tsc. This activates the TypeScript compiler using the settings defined in our tsconfig JSON file. So what does it do? Well, this command scans the src folder for any ts files and compiles them into JavaScript files that will be placed in a new folder called dist. This step is essential because TypeScript needs to convert your TypeScript code into standard JavaScript, which can be executed in a runtime environment like Node.js. So it's really important. Now let's execute the compiled JavaScript file. Simply run the command node dist/index.js. This is where the magic happens. When you execute this command, the output will show hello TypeScript, which confirms that our code is not just syntactically correct, but also functioning as we intended it to. This process of compiling followed by execution is critical in TypeScript development, as it allows us to catch errors early and really leverage the benefits of TypeScript's type system, while ensuring our final output is all set in JavaScript, ready for deployment or further development. And congratulations, you've successfully set up a TypeScript project and witnessed the fruits of your hard work. Now let's dive into how we can enhance our type safety while working with popular JavaScript libraries that unfortunately don't have TypeScript support. So, to kick things off with Express.js in our TypeScript project, we first need to install its type definitions, which you can find in the definitely typed repository. This step is super important because having type definitions allows TypeScript to understand the shapes of objects and functions from third-party libraries, making sure we catch errors at compile time and not when our code is running. To do this, we're going to execute a command to install the @types_express package as a development dependency. This package brings in the necessary type definitions specifically for Express.js, and trust me, it gives us handy auto-completion features and type checking while we build our apps. Now, by using the savedev flag, we indicate that this dependency is just for development. It won't bloat our production build. So adding this little package is gonna greatly improve our coding experience and help keep our interactions with Express.js type safe, making our code not only more robust, but also a lot less prone to pesky errors. Now let's dive into implementing the server-side configuration for our TypeScript project. In this tsconfig JSON, we specify some crucial options for compiling TypeScript code tailored specifically for a Node.js environment. Here, the target is set to ease next, which allows us to tap into the latest JavaScript features. Meanwhile, the module is configured to use commons, the module system that Node.js loves. The root dia is where it all begins. It indicates the directory of our TypeScript source files, and we're setting that to the current directory, which we indicate with. Now, for the out dia, that's going to point to where all our compiled JavaScript files will hang out, specifically in a folder called dist server. And let's not overlook the inclusion of types, which tells TypeScript to load the Node.js type definitions. This is super important as it enhances our development experience, giving us type support for those Node.js specific features we might need. Now moving on to the client-side configuration here, we're still using easeNext for the target, but we'll set the module to easeNext as well, since that's friendly with modern browsers. The lib option here includes DOM, which helps TypeScript understand types specific to web APIs. In short, this setup ensures that both our backend and front-end TypeScript code is not only properly configured, but also optimized for their respective environments. Now let's implement a build script in our package JSON file. This simple yet effective addition makes it super easy to compile our TypeScript code. Just by adding the line build TSC within the scripts section, we create a custom command that runs the TypeScript compiler, also known as TSC. So instead of typing npx tsc into the terminal every single time, you can just run npm run build. This shortcut not only streamlines your workflow, but also cuts down on those pesky typographical errors. Each time you want to compile your code, you can effortlessly run this command, providing you with a smoother development experience. This approach really highlights the importance of managing scripts in package JSON, as it organizes essential project tasks in a way that enhances both efficiency and clarity in your development process. So keep this practice in mind as your project scales, because you'll find that having organized scripts is invaluable for maintaining productivity over time. We wrap up our project setup journey in TypeScript. Remember, this is just the beginning. There are vast landscapes to explore, from generics and decorators to advanced types and integrating with modern frameworks. TypeScript wonderfully enhances JavaScript development, making your codebase not only more robust but also more maintainable and enjoyable to work with. So keep practicing, and soon you'll find that writing TypeScript feels like second nature. So, are you ready to dive deep? Your TypeScript adventure. Now let's explore type annotations in TypeScript and how they can really enhance our function definitions for better type safety. To kick things off, we have this basic JavaScript function that takes two parameters and returns their sum. But here's the catch: this function doesn't enforce types, which makes it a bit vulnerable to bugs if, say, a non-numeric value slips through. So let's level up by writing an improved version using TypeScript. Here we explicitly declare that both parameters must be of type number, and we also specify that the return type is a number. This small adjustment means if someone tries to pass, well, a string or any type other than a number, TypeScript will raise a compile time error. That's pretty awesome because it helps us avoid potential runtime issues. By applying these type annotations, we're not just clarifying our intent, we're really tapping into TypeScript's strength to catch errors during development. It makes our code much more reliable overall. This practice helps us steer clear of those chaotic situations where unexpected types may lead to confusing bugs. Ultimately, it gives us a smoother and more predictable coding experience. Now let's see how we can leverage TypeScript to enforce type safety for arrays. In JavaScript, when you create an array, it can accept elements of any type, which can lead to potential issues down the line. For example, initially we define an array of numbers simply as const numbers equals. While this works, it doesn't prevent someone from accidentally adding a string like 6 to it, which creates confusion and potential runtime errors. To avoid this, we can explicitly declare the type of the array in TypeScript as number. This ensures that the array can only hold numeric values. So when we initialize the numbers array this way, any attempt to push a non-numeric value, such as 7, will raise a compile time error. This feature acts as a safety net, catching mistakes early in the development process. By annotating the type, we clarify our intent, and TypeScript helps enforce these rules, ensuring that our array behaves as expected and really enhances overall code reliability. Now let's take a look at how we can define an interface for a user in TypeScript. The code begins with the declaration of an interface named user, where we specify the required properties that every user object must have: an id of type number, a name of type string, and an email of type string. This really defines the structure that TypeScript will enforce for any object adhering to this interface. Next, we create a user object that complies with the user interface. Here we initialize a constant called user, assigning it a unique ID, a name, and an email that match the defined interface's structure. By doing so, TypeScript ensures that all the properties are present and correctly typed. Now let's see how we might implement a scenario where a developer mistakenly omits a required field. In this case, when we attempt to define another user object without the email, TypeScript will raise a compile time error. This feature showcases one of TypeScript's strengths. It acts as an early warning system to prevent potential issues and enhances code reliability. By using interfaces, we not only create clear contracts for our data structures, but also foster better collaboration among developers. Now let's take a look at how to implement a greeting function in TypeScript using proper type annotations. The first version of our function, written in plain JavaScript, defines a greet function that takes a user parameter and returns a greeting string. Here, the function relies on the assumption that the user object will have a name property, and this can lead to issues if an incorrect object is passed. To enhance this, we can tighten our type checks by specifying the type of the user parameter. In the second version, we redefine the greet function to accept only objects that conform to a user interface, which ensures that the name property exists and is, you guessed it, a string. Additionally, we specify that the function returns a string. This explicit typing guarantees that any call to the function with an invalid user object will raise a compile time error, preventing potential bugs and ensuring that the function behaves as expected every time it's called. Through these enhancements, TypeScript helps us maintain type safety and clarity in our code. Now let's take a look at how we can implement union types in TypeScript. Union types allow us to define a variable that can hold multiple specific types, which really increases the flexibility of our code. For instance, we can define a function, let's call it printed, that accepts an argument called id, which can either be a number or a string. By explicitly stating that id can be of type number or string using the union type notation, TypeScript ensures this function can safely handle both types of inputs. This is a significant enhancement over plain JavaScript, where you wouldn't restrict the type, potentially leading to unexpected behaviors. With our TypeScript implementation, we can call printed with a number, say 123, or a string like ABC. Both of those are valid calls. This capability really showcases how union types allow for safer and more predictable code by enabling inline type checking, which helps us catch potential errors early on in the development process. By adopting such practices, we enhance the overall robustness and maintainability of our applications. Next, we will implement a custom declaration for the Lodash library to enhance our type checking capabilities. Now you see, TypeScript may not have type definitions available for all third-party libraries. So what we can do is create an ambient declaration to define the types we need. In this case, we utilize the declare module syntax to specify that we're adding types for the Lodash module. Within this declaration, we define the structure of the chunk function. It indicates that it takes an array of any type and a size parameter, returning a two-dimensional array containing chunks of the specified size. This approach allows TypeScript to understand how to handle the chunk function, ensuring that when we use it in our code, we enjoy the benefit of type safety and can catch any issues right at compile time. Now, let's make things even simpler. We can install community-maintained type definitions from definitely typed. By running the command to install at type/Lodash, we can automatically fetch the predefined type definitions for Lodash. This frees us from manual declarations and enables us to really leverage TypeScript's safety features more effectively. This way, we can work with Lodash functions seamlessly, all while maintaining robust type checking in our TypeScript project. As you become more familiar with TypeScript and its type checking features, you'll start to really appreciate the impact they have on your development process. In addition to catching those pesky errors, type checking can also improve your code documentation, which makes it easier for others to get a grasp on how to work with your code. This is especially beneficial when you're part of larger teams. With TypeScript, you're not just writing code, you're actually laying down a solid foundation that clearly communicates your intentions, aids in development, and ultimately leads to high-quality outcomes. So think of it like building a sturdy house. With a proper structure, thorough documentation, and well-defined materials, you're set for success when it's time to welcome in those tenants. In conclusion, basic type checking will really set you on a path towards writing more robust and maintainable JavaScript code through TypeScript. So far, we've learned how type checking in TypeScript works to reduce errors and enhance the developer experience. We also explored lots of important concepts like arrays, interfaces, function types, union types, and how to handle types from libraries. Now, it's time to roll up our sleeves and get our hands dirty. I truly encourage you to incorporate these type checking features into your next project and experience firsthand just how much smoother development can be. Thank you for tuning in today. Many developers rely on open source libraries to enhance their projects, but these libraries are often written in JavaScript, and they might not include TypeScript typings. This could create a bit of a hurdle when you're keen on leveraging the benefits of type checking and type safety that TypeScript provides. Today, we'll dive into how to load types from definitely typed to bridge this gap effectively. So far, we have uncovered how TypeScript enriches JavaScript by introducing a type checking mechanism that, reduces errors and enhances the overall developer experience. We've also explored key concepts like arrays, interfaces, function types, and union types, which are essential in enforcing structure and ensuring type safety in our code. Additionally, we discussed how to manage type definitions for third-party libraries, making integration a whole lot smoother. Now let's shift our focus to loading types from definitely typed, so you can streamline the process of using JavaScript libraries in your TypeScript projects. Now let's implement the following command to set up Node Package Manager, or NPM, in our project. When you run npm init it initializes your project with a default configuration, creating a package JSON file automatically. Now this file is super crucial. It serves as the backbone for managing your project's dependencies, scripts, and metadata. By opting for the Y flag, you're enabling npm to generate this file with all the default settings, skipping any interactive prompts, which, let's be honest, can save time. This streamlined approach is especially great for developers who want to set up their projects quickly without dealing with extensive configuration details at this stage. Once you execute this command, you'll have a structured way to install and manage other packages, including any type definitions you might need from Definitely Typed. This step is essential for ensuring your TypeScript project can effectively utilize JavaScript libraries while maintaining type safety, all of which helps optimize your development workflow and reduces potential runtime errors later on. Now let's dive into how we can implement a simple Express server using TypeScript. First off, we need to import the Express library, which gives us a robust framework for building our web applications. Once we've got that imported, we create an instance of Express, which we'll call app. This acts as our main application object. Pretty neat, right? Next, we'll define a root using app-get. Here we specify the root URL, which is just the /, and then we provide a callback function that takes two parameters, rec and res. Now, just to clarify, rec represents our request object, while res stands for the response object. Within this function, we send a simple string back to the client, confirming that our server is up and running. Finally, we call applisten to start the server on port 3000. This function also takes a callback that logs a message to the console, letting us know the server's active URL. By setting up this basic server, we not only showcase how to serve content with Express, but we also highlight the power of TypeScript's type safety. With the right type definitions installed, we can make sure that the request and response objects are properly typed, which significantly reduces potential runtime errors. So there you have it, a simple yet effective Express server with TypeScript. Now let's see how we can implement a basic Express server without using TypeScript definitions. In the code we have here, we start by importing the Express library, which is absolutely fundamental for creating web applications in Node.js. So the first thing we do is create an instance of the server using Express, which initializes our application. Next up, we establish a root with the app-get method, which listens for GET requests on the root URL, so that's just the / or slash. And in our root handler, we simply send back a text response that says hello without types. But here's where it gets interesting. Without type definitions installed, TypeScript is going to raise an error about the request and response parameters. This is because TypeScript just can't infer the types of rec and res, and that leads us to a lack of type safety when we're handling these objects. This example really highlights how crucial typings are, as they help us avoid potential errors that could arise from not properly managing our request and response. So it's super important to install the corresponding type definitions to harness the full power of TypeScript in enhancing our development experience and ensuring that our code remains robust. Now let's explore how we can define type declarations for a hypothetical library, mycoollib, that lacks official TypeScript definitions. To start, we'll create a DTS file, which allows us to declare the module and specify the types we'll be using. In our example, we'll declare that the library contains a function called coolFunction, which takes a string as an argument and returns a number. By defining the module this way, we effectively inform TypeScript of the expected structure and types of mycoollib, enabling type checking and auto-completion features for this function. Next, we'll import coolFunction from our newly defined module and invoke it using a string input TypeScript rocks. Here's the cool part. While we're calling this function, we're also specifying that the returned value should be of type number. This approach, you see, ensures that even without official typings, we maintain type safety in our application, which reduces the risk of runtime errors and enhances the robustness of our code. So, we can comfortably utilize third-party libraries while still adhering to TypeScript's strong typing principles. Now let's dive into how we can search for typings in the Definitely Typed repository. To find those available type definitions for a specific library, you can actually use the npm search command, which, by the way, is a really convenient way to access all this information directly from your command line. So let's say you're interested in locating the types for that popular utility library, Lodash. You'd simply run the command that specifies searching for @types/Lodash. Executing this command lets you see various results tied to the typings for Lodash. This step is crucial because having the right type definitions not only makes your coding experience smoother, with awesome autocomplete suggestions and type-checking features, but it also helps you dodge those pesky runtime errors. Once you've identified the right package, you can go ahead and install it using npm. This step integrates the type definitions into your project seamlessly. By doing this, you're really ensuring that you can fully leverage TypeScript's capabilities for type safety, which ultimately enhances the overall reliability and maintainability of your code, especially as you work with the Lodash library in your application. So that's a quick overview of the process. Now let's dive into how we can work with arrays using Lodash, which is this amazing utility library for JavaScript. First, we need to import Lodash into our TypeScript file. This gives us access to all its cool features. Next, we're going to declare an array of numbers called numbers, which will hold the integers from 1 to 5. We'll annotate this array as number, ensuring that TypeScript helps us by enforcing type safety, so only numbers are allowed in this array. Now let's take a look at how we can use the reverse function from Lodash to reverse our array. The reversed array will be stored in a new variable called reversed, which we'll also type as number. This way we can be sure that the output maintains the same numeric type as our input. Finally, just to see the result, we'll log the reversed array to the console. You should expect to see an array displaying the numbers in reverse order. It's really great how Lodash simplifies our array manipulation while sticking to TypeScript's strict type-checking mechanisms. By enforcing proper typing, if we mistakenly try to pass a non-numeric value to the reverse function, TypeScript will alert us at compile time, helping us keep our code neat and error-free. Now let's take a look at how using Lodash without types can lead to unforeseen issues, shall we? In this example, we begin by importing Lodash, a powerful utility library that simplifies operations on arrays, objects, and collections. We then create a mixed array that includes numbers and a string, which is intentionally incorrect for our intended purpose. When we call the Lodash reverse function on this mixed array, TypeScript identifies that we are attempting to reverse an array with improper types. However, without the typings installed, it can't provide a specific warning about the presence of the string for. This, my friends, demonstrates a critical downside of lacking type definitions. The risk of runtime errors goes up significantly because the type safety net that TypeScript offers is absent. Finally, while we log the reversed array, the output may still include the string, leading to potential confusion and bugs later in the code execution. This example underscores the importance of installing type definitions, as they not only prevent accidental type mismatches, but also serve as essential documentation, fostering better coding practices and a deeper understanding of the codebase. Let's touch on some fantastic tools that can really elevate your TypeScript browsing and exploration game, shall we? One incredibly valuable tool to have in your arsenal is the TypeScript Playground. It's this amazing online editor where you can test TypeScript code snippets in real time, no setup required. Imagine being able to mock the usage of library functions and types while also getting immediate feedback on how everything works together. You can experiment with random functions or create mock implementations of your types right there, which is a great way to grasp the proper usage scenarios before you dive deep into your own editor. Now let's talk about another handy tool, VS Code. It offers rich integration with TypeScript, which means it can auto-import definitions for you and suggest types based on your library installations, even those gems from the definitely typed repository. This is super helpful as you navigate through complex interactions in your projects. By leveraging the robust combination of TypeScript typings and IDE support, you'll stay focused and effective. This ensures that the code you write is not just precise, but also free from those pesky errors. To wrap it all up, using definitely typed to load types into your TypeScript project is an essential step in ensuring robust application development. We've covered how crucial these type definitions are, how to acquire them using npm, and what to do if a particular library lacks built-in typings. Remember, even if a library is commonly used, always check for the availability of typings. If you find they're missing, don't hesitate to create your own typings. Through all these steps, you'll continue to enjoy the benefits of enhanced type safety, which means fewer bugs, clearer code, and a smoother developer experience. So go forth and confidently integrate your favorite JavaScript libraries into your TypeScript projects, ensuring they're backed by adequate type definitions. Happy Getting started with TypeScript is an exciting journey. Today, we're diving into project setup, a crucial step that allows you to utilize TypeScript effectively in your applications. So far, we've learned how TypeScript provides type checking, enhancing our developer experience with concepts like arrays, interfaces, and function types. we discussed the importance of managing type definitions for JavaScript libraries using definitely typed to maintain type safety and prevent runtime errors. Additionally, we're also exploring how to install typings via npm and the perks of using type definitions for popular libraries like Express and Lodash. Overall, ensuring proper type definitions leads to more robust applications and a smoother coding process. Now, we will cover how to set up TypeScript in your projects, exploring different methods of integration based on your specific needs. Let's get into it. Now let's take a look at setting up our folder structure and creating our initial TypeScript file. First, we're going to create a folder named src. This will hold our TypeScript source files. Keeping things organized is really important in any project, so this step is essential. Inside that src folder, let's create a file called index.ts. This is where we're going to write our TypeScript code. Next up, we'll implement a simple function called greet. This function will accept a parameter name of type string, and it will return a greeting message. Using type annotations here is a real game changer. It enhances type safety and ensures we're only passing valid arguments to our function. To show how this works, let's create a constant variable named user, setting it to student. Then we'll call the greet function with this variable, and voila, you should see the greeting message pop up in the console output. By using TypeScript, we're gaining the valuable advantage of type checking at compile time. This helps us catch potential errors early in the development process, which means a smoother and much more reliable coding experience. Now let's implement a simple greeting function in our TypeScript file. We'll begin by defining a function called greet that takes one parameter, name, and it has to be of type string. This is super important because it ensures we're only passing a string value, which helps us maintain type safety. The function, once called, returns a greeting message that includes the name we provide, showcasing how TypeScript allows us to easily manage data types. Next, we create a constant variable named user, and we assign it the value student. That's going to be the input for our greet function. Now let's use console.log to output the greeting message by calling greet user. This is a great way to see how functions can take arguments and display outputs in the console, making it all easy to watch in real time. Once we've got our TypeScript code ready, we'll need to compile it into JavaScript. This is where the TypeScript compiler comes in. It translates our TypeScript code into JavaScript that can run in any browser or Node.js environment, and that's how we can keep things efficient and organized. Now let's take a moment to intentionally introduce a type error in our TypeScript code. We start with a function called greet, and it's designed to accept a parameter named name, you guessed it, of type string, and it will return a nice greeting message. Now the TypeScript compiler is pretty smart. It ensures that the argument we pass to this function matches the expected type. But to really see TypeScript's type safety features in action, we're going to tweak the code a bit. Next, we're going to introduce a variable called user, but instead of assigning it a string value, we'll mistakenly set it to a number 42. So when we call the greet function with this variable, we're deliberately creating a type mismatch. Now here's where it gets interesting. When we run the TypeScript compiler, we get to observe that powerful feedback mechanism at work. The compiler will throw an error indicating that user is not assignable to the parameter type string. This example really highlights how TypeScript helps catch those potential bugs during development, ensuring that we adhere to our specified types and ultimately leading to more reliable and maintainable code. Now let's see how we can seamlessly integrate TypeScript into our existing JavaScript project. To kick things off, we first need to install TypeScript as a development dependency in our project. This crucial step ensures that TypeScript is available in our codebase, letting us leverage its powerful type-checking features. Next, if we're already using JavaScript libraries in our project, which is quite common, it's essential to also install the necessary type definitions for those libraries. For instance, if you're working with React, adding the type definitions for React and React DOM will really boost type safety and help the TypeScript compiler understand the types linked with these libraries. Once we've got those dependencies installed, we'll need to create or adjust our tsconfig JSON file. In this configuration, we're going to include both TypeScript and JavaScript files for a smooth transition as we migrate to TypeScript. By specifying the include option to cover all JavaScript files along with TypeScript files, we allow for an easygoing shift where we can convert files one step at a time while keeping our existing JavaScript code in play. This setup will definitely streamline our development process as we blend TypeScript and JavaScript in our project. Now let's dive into how we can implement a simple function in TypeScript. Initially, we have a basic JavaScript function called add that takes two parameters, a and b. Now in this version, both parameters are declared without any type annotations, meaning they can accept any data type, which can be quite flexible, but it also brings some uncertainty along with it. When we convert this to TypeScript, we want to be a bit more specific. So we need to explicitly define the types we expect for both parameters and also for the return type. In our TypeScript version, we'll modify the add function by including type annotations for R and B, specifying that they should be of type number. Additionally, we'll annotate the return type of the function as number2, which helps to inform both the developer and TypeScript that this function will always return a numeric value. This enhancement not only improves clarity and maintainability, but it also ensures type safety, helping to reduce potential errors during runtime. By adopting such practices, you can gradually convert your JavaScript code into TypeScript, reinforcing the benefits of static typing as you progress. It's a great way to make your code more robust and reliable. Now let's implement a build script in our package, JSON, to simplify the TypeScript compilation process. In the scripts section, we'll add a new entry called build that will trigger the TypeScript compiler or TSC whenever we run the command. This single command allows us to compile all our TypeScript files effortlessly, and it outputs the resulting JavaScript files into the designated dist folder, which helps keep our project organized. Next, we'll also set up a watch mode by including another script entry called watch. This option enables automatic recompilation of TypeScript files whenever we make changes. It really enhances our development workflow by providing immediate feedback. When we run npm run watch, it keeps the TypeScript compiler active, always monitoring for any modifications in the code. This saves us from having to manually execute the compilation process every time we update our files. So, this combination of build and watch scripts truly streamlines our development experience. It ensures we can focus much more on writing code and worry a lot less about the compile step. Now let's see how we can set up Jest for testing in our TypeScript project. First, we're going to install Jest along with its TypeScript support, which includes tsJest and the type definitions for Jest. This step is crucial as it ensures our test environment knows about TypeScript features, allowing us to write tests using TypeScript syntax. Next, we need to create a configuration file for Jest. We'll name it jest.config.js, and here we specify the preset as tsJest and the test environment as node. This configuration enables Jest to work seamlessly with TypeScript files, setting up the appropriate testing environment. Now, let's create a test file in our src directory. We'll kick things off with a simple test for our add function to ensure that it performs as expected. In this test file, we'll import the add function and write a test case that checks whether adding 1 and 2 returns 3. This straightforward test serves as a basic demonstration of how to validate that our functions behave correctly. To make running our tests more convenient, we'll add a script to the package, JSON, that allows us to execute Jest directly from the command line. This integration into our workflow is essential to maintain code quality and catch any issues early in the development process. Now let's take a look at how to define a user structure utilizing TypeScript's powerful interface feature. We begin by declaring an interface named user, which explicitly outlines the properties that a user object should have. In this case, our user interface contains two properties, name, which is of type string, and age, which is of type number. So let's move ahead. Next, we implement a function called printUser that takes a parameter of type user. This function illustrates how we can pass objects that conform to our defined structure. Inside the function, we use console.log to output the user's name and age, showcasing how TypeScript enforces the defined types and helps in accessing object properties safely. Now finally, we create an object named user that adheres to the user interface, providing relevant values for name and age. By calling the printUser function with this user object, we can see how our code effectively utilizes TypeScript static typing to ensure correctness and clarity. This leads to a more maintainable and comprehensible code base, as each piece of data is well defined. In conclusion, setting up your TypeScript project can actually be pretty straightforward, whether you're starting from scratch or integrating TypeScript into an existing JavaScript codebase. We've walked through the process of installing and configuring TypeScript, creating compatibility between TypeScript and JavaScript, introducing testing, and following best practices. Just remember, the confidence and clarity you gain from using TypeScript will not only enhance your coding experience, but it'll also lead to more robust applications. As you continue this journey through TypeScript, your next steps will be to dive deeper into the nuances of the type system and explore some advanced features. So let's keep this exciting adventure going. Now let's take a look at a simple example of a function that greets a user. Initially, we define a function called greet that takes a parameter user without specifying its type. This means it can accept any data type, allowing it to run without throwing errors even if we pass a number instead of a string. In our example, when we call greet with the value 42, it concatenates it with the string hello. While this may work without errors, the output is not what we might expect because the function is designed to greet users by their names, which are typically represented as strings. Now let's see how we can implement type safety through TypeScript. By defining the parameter user with the type string, we ensure that only string values are accepted. When we attempt to call this updated function with 42, TypeScript will trigger a compile time error, indicating that we provided a number instead of a string. This enforcement of type checking helps prevent unexpected behavior and bugs in our code, ultimately leading to cleaner and more reliable software development practices. Next, we will write a simple function to calculate the sum of two numbers. This JavaScript function takes two parameters, a and b, and returns their sum. However, there is an important caveat. If either parameter is a string, JavaScript will concatenate the values instead of performing arithmetic addition. For instance, passing the strings 5 and 10 to the function will result in 510 rather than the expected numeric sum of 15. This potential for error highlights the limitations of JavaScript's dynamic typing. Now let's implement the same function in TypeScript by explicitly defining the types of our parameters. By declaring both a and b as numbers, we ensure that only numeric values can be passed to the function. This change not only prevents the function from accepting strings, but it also enables TypeScript to raise a compile time error when incorrect types are provided. Consequently, our function becomes more reliable, avoiding unintended behavior caused by type mismatches. Now, when we invoke the function with numbers, we receive the expected result every time, showcasing the enhanced type safety that TypeScript offers. Now let's see how we can define a user object in TypeScript. We begin by creating an interface named user, which specifies that any object of this type must have a name property as a string and an age property as a number. This strict definition ensures that any function using a user object will receive the necessary properties, promoting type safety and preventing runtime errors. Next, we implement a function called printUser that takes a user object as an argument. Inside this function, we access the name and age properties and log them to the console. The utility of this structure is evident when we create a valid user object with both properties and call printUser with it, demonstrating its expected behavior. However, TypeScript also allows us to enhance our interface by making properties optional. By adjusting the user interface to mark age as optional, we maintain flexibility. This means we can call printUser with just the name property present, ensuring our function remains resilient and adaptable, catering to scenarios where not all user information is available. Now let's see how to create a function that processes an array of numbers. We define the calculateTotal function, specifying its parameter as an array of numbers using the type annotation number. This ensures that only numerical values are accepted, enhancing type safety. Inside the function, we utilize the reduce method to accumulate all the numbers in the array, starting with a total of 0. The reduce method iterates over each number, summing them up to yield the final total. By implementing type checks, any attempt to pass an array containing non-numeric values, like a string alongside numbers, will result in a compile time error, reinforcing code reliability. Next, we can denote a tuple to represent a user, which combines both a string and a number. The user tuple type ensures that we adhere to a specific structure by requiring the first element to be a name string and the second to be an age number. When we create a user using the createUser function, TypeScript will verify that we pass the expected tuple format. If the order of elements is incorrect, the compiler will flag an error, highlighting TypeScript's efficiency in maintaining strict data structures and enhancing code integrity. Now let's explore how we can implement union types in TypeScript, which allow a variable to hold multiple types. We'll start with the function printed, which accepts an argument that can be either a number or a string. This flexibility is particularly useful when the function is expected to handle various types of identifiers, such as numeric IDs and user names. The function logs the provided ID to the console, showcasing its versatility. If we were to pass in any type other than a number or string, TypeScript would alert us with a compile time error, ensuring that we maintain strict control over the data types being used. Next, we'll take a look at type assertions with the variable random value. Here we declare random value as any, meaning it can hold any type. We then assert that random value is actually a string, enabling us to access its properties safely, in this case, the length property. This assertion is a powerful feature that helps the TypeScript compiler understand our intentions, although it requires us to be cautious, as an incorrect assertion could lead to runtime exceptions. This demonstrates the importance and flexibility of type safety in TypeScript. Now let's take a look at how we can leverage generics to create versatile functions. The log value function we are about to implement utilizes a type parameter, denoted as t, which acts as a placeholder for any data type. This means that when we call this function, we can specify a type like number or string, ensuring that the value we pass in is actually of the type we've designated. For example, we can call log value with a number, such as 123, and it will correctly output its value. Similarly, if we use a string like hello world, the function will output that string as well. This flexibility highlights one of the key strengths of TypeScript. It provides compile-time type checking while still allowing for varied data types through generics. Thus, developers can write more reusable and type-safe code, making it easier to maintain and reducing the likelihood of runtime errors. By embracing this feature, you enhance the robustness of your applications as you handle different data types seamlessly. Now let's see how we can integrate TypeScript with existing JavaScript libraries by installing type definitions. When working with libraries like Lodash, it's crucial to ensure TypeScript can understand the library's functionality and types. To do this, we can utilize the @types namespace available on npm, which hosts type definitions for many popular JavaScript libraries. Next, we will write the following command to install the Lodash type definitions: npm install @types/lodash-save-dev. This command adds the necessary type information to our project, allowing TypeScript to check our use of Lodash functions. With the type definitions in place, we can leverage TypeScript's robust type-checking features, even when using third-party code. This integration not only enhances code reliability, but also provides auto-completion and documentation within IDEs, improving our overall development experience. By adopting these types, we ensure that any interaction with Lodash's APIs adheres to the expected types, catching potential errors during compilation rather than at runtime. This is a vital step toward creating safer and more maintainable applications while using external libraries. As we conclude this discussion, remember that adding type checking to your JavaScript projects using TypeScript is a strategic move. It improves code quality by catching errors at compile time instead of runtime. Transitioning can be smooth, especially when done gradually, taking advantage of TypeScript's features like interfaces, union types, and generics to create robust, maintainable applications. By understanding and applying type checking through TypeScript, you're on your way to becoming a more effective developer, minimizing bugs and enhancing your coding experience. In future lessons, we will delve deeper into TypeScript's advanced features and how they can empower you to write high-quality code effortlessly. Next, we will write the commands to create and initialize our project directory. We begin by creating a new directory called fullstackapp and navigating into it. This sets up a dedicated space for our project. We then execute npm init-y, which generates a package, JSON file with default settings, laying the groundwork for managing our application's dependencies. Now let's implement the installation of necessary packages by running a command that installs TypeScript and Express. TypeScript will enhance our JavaScript with type safety, while Express will serve as our web framework for building the server. The additional command installs type definitions for Node, JS, and Express, providing TypeScript with the necessary information to understand these libraries in our project. Next, we'll create a tsconfig, JSON file using the TypeScript compiler's initialization command. This configuration file instructs the TypeScript compiler on how to compile the project. We will configure the compiler options to target modern JavaScript ES6 and enable strict mode, ensuring we're utilizing TypeScript's features fully while keeping our code organized by specifying which files to include and exclude during compilation. Now let's see how we can implement the server-side code to set up our Express application. We start by importing the Express package, which is a minimal framework for building web applications in Node.js. We create an instance of the Express application and set up a constant for the port, defaulting to 3000 if no environment variable is provided. This allows our server to listen for incoming requests. Next, we define a basic route for the route path using the app-get method. This route responds to HTTP GET requests and sends a greeting message back to the client, indicating that the server is operational. Following that, we call app-listen, which starts the server and instructs it to listen on the specified port. A callback function is provided to log a message to the console, confirming that the server is running and providing the URL to access it. Now let's specify a script in our package JSON file. This script will make it easy to start the server using TypeScript node TS node, allowing us to run our TypeScript files without needing to compile them to JavaScript explicitly. Finally, we can run the server using npm start, and upon visiting the given URL, we will see the greeting message served by our backend. This sets the stage for further enhancements and functionality on the server. Now let's implement the HTML structure for our client-side application. We create an index HTML file which serves as the main entry point for rendering our front end. This structure begins with the doctyp HTML declaration to define it as an HTML5 document. The head section includes essential metadata like the charset and viewport settings to ensure proper rendering on different devices. We've given our page a title, Full Stack App. Inside the body, we define a div with the id app, which acts as a placeholder for dynamic content injected by our JavaScript code later. To link our JavaScript bundle to the HTML, we include a script tag that points to bundle.js in the dist directory, where our client-side logic will reside after being transpiled from TypeScript. Next, we will write the TypeScript logic for fetching data from the server. In app.ts, we define an asynchronous function called fetchData. This function initiates a GET request to the server's root path, retrieves the greeting message, and updates the inner text of the app div with this message. Notice the use of the non-null assertion operator, which assures TypeScript that the app element exists, ensuring that our DOM manipulations are safe and error-free. This foundational setup allows our front end to dynamically interact with the back end smoothly. Now let's implement the necessary configurations to bundle our TypeScript front-end code using Webpack. First, we install Webpack and its related packages, including the Webpack CLI for command line usage and TS Loader to handle TypeScript files. This allows us to compile TypeScript into JavaScript effectively. Next, we create a configuration file named webpack-config.js at the root of our project. In this file, we set the mode to development to facilitate easier debugging. We specify the entry point for our application as app.ts, located in the src/client/src directory. This is where Webpack starts the bundling process. Additionally, we define the output properties, specifying that the bundled JavaScript file should be named bundle.js and placed in the dist directory. The resolve section ensures Webpack recognizes file types such as TSX, TS, and JS. Finally, in the module section, we establish rules for processing TypeScript files using TS Loader, instructing Webpack to apply this loader for all files ending in TS while ignoring the node modules directory. To integrate this into our project, we add a new script in package JSON that allows us to run the build process easily. Whenever we execute npm run build, Webpack compiles our TypeScript code and generates the bundled JavaScript file ready for deployment. Next, we will implement a crucial feature that enables our Express server to serve static files. This is done by using the Express static middleware, which tells the server to look for files in a specific directory. Here, we will configure it to serve from the dist directory located in our client folder. By using the path join method, we ensure that our application remains platform agnostic, meaning it will work on various operating systems without issues related to file paths. This setup allows the server to directly serve the bundle.js file generated by our front-end build process, making it accessible via a simple URL request. Following this, we will run our server with the command provided, initiating the backend functionality. Once the server is up and running, we can open the index.html file from the client directory in any web browser. If everything is set up correctly, we should see the greeting message dynamically loaded from our server. This integration beautifully demonstrates how the front end and back end communicate in a full stack application setup, reinforcing the power of our established TypeScript and Node.js environment. Now that we have the basic setup working, let's expand our application by adding a new API endpoint. This endpoint will allow the front end to interact with the back end dynamically by returning a JSON object. We will define this API route in our index.ts file. The app-get method sets up a route handler for the /API/data endpoint. When a GET request is made to this endpoint, the server responds with a JSON object that contains a message and a status. This response can be incredibly useful for updating the front-end content in real time. Next, we will implement the client-side functionality to fetch this API data. We'll create an asynchronous function named fetchAPI data. In this function, we use the fetch API to make a request to our newly created API endpoint. After receiving the response, we parse it as JSON and then update the content of the HTML element with the id app to display the message provided by the API. This integration allows our front end to reflect the latest data from the server every time the page is refreshed, creating a dynamic user experience. Now let's implement error handling to ensure our application responds appropriately to unexpected situations. On the server side, we can catch expired routes or server errors using middleware. In our index.ts file, we add a middleware function that will handle requests that do not match any defined routes. This function will send a 404 not found response, informing the user that the requested resource could not be located. It's positioned towards the end of your middleware stack to ensure it captures any unmatched routes after all other routes have been attempted. Next, we'll see how we can enhance the client-side functionality by updating our fetch function to manage errors gracefully. In our app.ts, we implement a try-catch block around our fetch operation. This allows us to attempt to retrieve data from the server's endpoint while catching any errors that may arise, such as network issues or server errors. If the fetch fails, we log the error and provide user-friendly feedback in the UI, notifying them that data retrieval was unsuccessful. This structured approach to error handling improves the robustness of our application and enhances user experience. As we wrap up our exploration of setting up a full-stack application, we should reflect on what we have built. From the server-side logic handling requests and serving static files to the client-side dynamically rendering data from the server, we've gone through a comprehensive setup that blogs together both front-end and back-end components using TypeScript. By now, you should feel confident in your ability to structure and build your own full-stack applications while leveraging TypeScript for enhanced code quality and reliability. You've learned about the intricacies of using tools like Node, JS, Express, and Webpack to facilitate communication between your server and client-side code seamlessly. Moving forward, the next step in your development journey could include exploring databases, authentication mechanisms, and advanced front-end frameworks that can integrate with your existing setup. There's always more to learn, and with the foundation laid here, you're well on your way to building full-fledged applications. Happy coding, and see you in the next. You want to get started with TypeScript? Fantastic. The big question is, how do you start? In this lesson, we will cover project setup fundamentals that will help you lay a solid foundation for your TypeScript applications. So far, we learned that setting up a full-stack application involves establishing a TypeScript environment to enhance JavaScript code with strong typing and structure. We've covered how to set up Node, JS, and Express for the backend, create a directory structure, and serve static files while connecting the front-end and backend with dynamic data fetching. Additionally, we learned the importance of error handling in our application to ensure robust communication between client and server. Finally, we explored the foundational components that will enable us to expand our application further with databases and advanced frameworks. Now we will focus on how to set up a TypeScript project from scratch. Now let's see how we can check if Node.js is properly installed on your machine. To do this, you will use the command node-v in your terminal. This command queries the version of Node.js that you have installed. If Node.js is set up correctly, the terminal will return the version number, confirming that the installation was successful. This step is crucial as Node.js serves as the runtime environment for executing JavaScript code outside of the browser, and it's a foundational requirement for any TypeScript project. Next, we will write the following commands to create a new directory for our TypeScript project. The command mkdir myTypeScript project will create a new folder named myTypeScript project. Afterward, by using cd myTypeScript project, we change our current working directory to this newly created folder. This setup ensures that all subsequent project files and configurations are organized within this specific directory, providing a structured environment for building your TypeScript application. Having a dedicated project directory helps maintain clarity and organization as you develop your project. Next, we will initialize our new Node.js project using npm nodes package manager. To do this, we'll execute the command to create a new package.json file with default settings. This file is crucial as it keeps track of the project's dependencies and scripts, providing a structured way to manage the project's setup. Upon running the initialization command, you will see a package.json file generated, which contains essential information about your project, such as its name, version, and main entry point. Now that the package.json is ready, let's install TypeScript as a development dependency. This step enhances our JavaScript code with strong typing and structured programming features, ultimately leading to cleaner and less error-prone code. After successfully installing TypeScript, we can verify the installation by running a command that displays the version of TypeScript currently installed. This allows us to confirm that everything is properly set up and ready for the development journey ahead. Now that we have TypeScript installed, let's configure it properly. First, we generate a tsconfig JSON file, which serves as the configuration for the TypeScript compiler, defining how the TypeScript code should be compiled into JavaScript. By running the command to initialize TypeScript, a default configuration is created, allowing us to adjust various options to suit our project's needs. Next, we will fine-tune some key properties in the tsconfig JSON. For instance, setting the target to ES6 ensures our output code adheres to the ECMAScript 2015 standard, which brings modern features to our compiled JavaScript. We specify the module type as CommonJS, which is suitable for Node.js environments, enabling module imports and exports. Enabling strict type checking enhances our code quality by catching potential errors during development, fostering good coding practices. Finally, we define the out_dir option to direct the compiled JavaScript files into the dist folder, keeping our project organized. This setup not only clarifies the compilation process, but also prepares us for a smoother development experience as we progress. Now let's see how we can implement a simple function in our TypeScript application. In our index.ts file, we define a function called greet that takes a string parameter named name and specifies that it will return a string. This demonstrates TypeScript static typing, which helps catch errors at compile time and encourages clearer code. Within the function, we use template literals to construct a personalized greeting message that includes the provided name. Next, we invoke the greet function with the argument TypeScript developer and pass its output to console.log. This allows us to see the greeting message printed in the terminal when we run our application, confirming that our TypeScript setup is working correctly. By utilizing TypeScript's type annotations, we ensure that the name parameter is always a string, promoting safer coding practices. With this basic structure, we can easily expand our code further, adding more functionality or complexity as needed. This marks our first practical example of combining TypeScript's typing capabilities with a simple function. Now let's see how we can enhance our TypeScript application by adding a useful library for handling date and time. First, we will install the datefns library using npm, which allows us to work with dates efficiently. By running this installation command, datefns will be added as a dependency in our package, JSON, ensuring our project can utilize its functions. Next, we will implement the library in our index.ts file. To do this, we will import the format function from datefns, which is designed to format JavaScript date objects into user-friendly strings. After importing, we'll create a new date instance representing the current date and time. Here, the format function takes this current date and formats it into a string that showcases the date in the yimmdd format. Finally, we use console.log to display this formatted date alongside a greeting message, demonstrating how easily we can manipulate and present date information with the help of datefns. By incorporating this library, we significantly improve the date handling capabilities of our application. Next, we will focus on setting up version control for our TypeScript project using Git. First, we initialize a new Git repository by running a command that creates a hidden Git directory in our project, allowing Git to track changes. This step is essential for managing code in collaborative environments, as it provides a history of all modifications. Now let's create a gitignore file to ensure that certain directories, like node modules, which contains our dependencies, and dist, where our compiled JavaScript files are stored, are not tracked by Git. This will keep our repository clean and prevent unnecessary files from being included in version control. After setting up our gitignore, we will stage all our changes using the command to add files to the staging area. This prepares our code for commit, which is like taking a snapshot of our project at this moment. Now, let's solidify our progress by committing these changes with a message that describes the state of our project. This process creates a checkpoint, allowing us to revert back to this state if needed in the future. Committing regularly helps maintain a comprehensive history of our project as we continue to develop and enhance our TypeScript application. Now let's move on to setting up Jest for testing our TypeScript application. First, we need to install Jest along with the tsjest package, which will allow our TypeScript files to be tested seamlessly. This is crucial as Jest will help us ensure our functions behave as expected, avoiding potential issues in the future. Next, we will configure Jest by adding a jest config.js file in our project's root directory. In this file, we are specifying that we want to use tsjest as our preset and that the test environment will be Node.js. This setup is essential for integrating Jest with our TypeScript code, ensuring thorough testing capabilities. Now let's create a new directory named tests to keep our test files organized. Within this directory, we will set up a file called greet.test.ts. In this test file, we will import our greet function and write a simple test case that checks whether the function returns the correct greeting message when called with a specific name, in this case, John. Finally, to execute our tests, we will run our jest command, allowing us to confirm everything works as anticipated. If the setup is correct, you will receive a reassuring message that all tests have passed. To wrap things up, project setup fundamentals in TypeScript is absolutely crucial for building efficient and maintainable applications. We have covered everything from initializing and configuring a TypeScript project to installing essential dependencies, using version control with Git, and ensuring code quality through testing. Remember, taking the time to set things up correctly can save you a lot of headaches down the road. It sets a solid foundation for your application development journey, empowering you to write clean, structured, and robust code using TypeScript. Now that you have this knowledge in your toolset, you are ready to explore more advanced topics and deepen your understanding of TypeScript. Next, we're setting up our project directory for the Express server. To do this, we start by creating a new folder named My Full Stack App and navigating into that directory. This is crucial as it establishes a separate workspace for our application, ensuring that our project files remain organized and contained. Now that we're in our project directory, we initialize a new npm project using the command with the Y flag. This automatically creates a package.json file, which will serve as the backbone of our project by managing dependencies and scripts necessary for our application to run efficiently. Once we have the project structure in place, we can proceed to install the required packages for building our Express application. This foundational setup will allow us to take advantage of TypeScript, enabling us to write type-safe code and making development smoother and more manageable. By properly structuring our project and using npm to handle dependencies, we're paving the way for a robust backend server that can scale and adapt to future development needs. Next, we will install the necessary packages to enhance our Express.js application with TypeScript support. To achieve this, we will execute the command to install Express, the type definitions for Express, and a few development tools. Express serves as the core framework for our server, while at Types Express ensures we have TypeScript definitions that help catch type errors at compile time, improving code safety. Additionally, we'll introduce tsnode to run TypeScript files directly and nodemin, which automatically restarts the server when file changes are detected, making our development workflow much smoother. Now let's move on to setting up our TypeScript configuration. We'll initialize a TypeScript project by running a command that creates a tsconfig.json file, which allows us to define how TypeScript compiles our code. We'll then open this configuration file to fine-tune the settings according to our project needs. Of particular importance are the out.dia, which instructs TypeScript where to place the compiled files, and the include setting that tells TypeScript to look for source files in the src directory, ensuring our development process leverages TypeScript's powerful features effectively. Next, we will write the directory structure for our application. We'll create a folder named src, which will house all our application code. This organization is crucial as it helps in maintaining clarity as the project grows. Inside the src folder, we will create a file named server.ts, which serves as the main entry point for our Express server. Now, let's implement the core setup of our server. First, we import the Express framework, which allows us to build our server effortlessly. We then instantiate an Express application. Using apt-get, we define a simple route for the root URL, which responds with a welcoming message. This basic endpoint demonstrates how we can set up routing with Express. Finally, we utilize the applisten method to instruct our server to start listening on a specified port, defaulting to 3000. This is generally where we would make our server accessible to incoming requests, and we also log a message to the console indicating the server is running. This foundational structure paves the way for further development by enabling us to handle additional routes and functionalities in our Express application. Now that we have our basic server set up, it's time to enhance its functionality with essential middlewares. We will implement body parser and cause to manage request bodies and handle cross-origin requests, respectively. First, we need to install these packages using npm. After installation, we will import body parser and cause into our server ts file alongside the express import. Next, let's write the necessary middleware configuration. By calling app use cause, we allow cross-origin requests, enabling our front-end to communicate seamlessly with our backend, especially during development where they may run on separate origins. Additionally, app use body parser JSON is crucial as it equips our server with the capability to automatically parse JSON request bodies. This functionality is vital for effectively handling incoming data from client requests. By implementing these middlewares, we ensure our server can robustly process incoming data while preventing potential issues associated with cross-origin requests. This setup lays a solid foundation for our Express server, allowing us to build more complex features as we continue our application development journey. Next, we'll write an API endpoint to handle user data using a POST request. In this section, we define a new route at /API/user that extracts the user information from the request body. The code begins by creating an instance of the user object based on the incoming request data. To ensure that the necessary fields are present, we check if both the name and email properties exist. If either of these fields is missing, the server responds with a 400 status code and an error message, indicating that both fields are required. This is crucial for maintaining data integrity and guiding the client on what is expected. On the other hand, if the validation passes, we send back a 200 status code along with a success message and echo the received user data. This not only confirms that the data has been successfully received, but also serves as a helpful response for the client, allowing them to verify their submission. This approach illustrates how to handle incoming data effectively, laying the foundation for more complex data management in our application. Next, we'll configure our package, JSON, to simplify the process of running our TypeScript server with NodeMin. By adding a start script in the scripts section, we enable the command npm start to initiate our server. This script utilizes NodeMin alongside tsnode, which allows us to run TypeScript code directly, and NodeMin ensures that our server automatically restarts whenever we make changes to the source files. This is especially useful during development, as it saves us the hassle of manually restarting the server. Now let's implement the command to start our server. By running npm start, we activate this script and the server begins to watch for changes, allowing for an efficient workflow. This setup encourages rapid development as we can make code adjustments and observe the effects immediately without interruption. Following this, we'll explore how to interact with our API. To do this, we can send a POST request to the /API/user endpoint, demonstrating how to send user data in JSON format using tools like curl. This shows us how our server processes incoming data and responds appropriately, marking a significant step in building our API functionality. Next, we will implement error handling in our Express application to ensure that any unhandled errors are properly managed. This is crucial for delivering meaningful responses to clients when something goes wrong. Now, let's see how we can add a middleware function to catch and log errors. This middleware function is defined using appuse, where we take 4 parameters, rec, res, and next. The first parameter, represents the error that has occurred within the application. Inside the function, we log the error stacked to the console for debugging purposes, which is extremely helpful when tracking down issues during development. Following that, we respond to the client with a status code of 500, indicating a server error, along with a generic error message stating, "Something went wrong." By doing this, we enhance the user experience by ensuring that even when errors occur, clients receive a clear indication that their request did not go as expected. Implementing this global error handling middleware is a best practice in building robust applications and is essential as our API grows in complexity. Now that we have our basic server set up, let's add a structured approach to building our API. First, we will create a folder named Routes, where we can keep our route definitions organized and separate from our main application logic. This helps maintain clarity, especially as the application grows. Once the folder is created, we will establish a new file called userroutes.ts to manage our user-related endpoints. In this file, we will import the router from Express and set up a router instance. Next, we define a post route at the root path of this router for handling user data submission. The route includes a function that checks if the required fields, name and email, are present in the request body. If either of these fields is missing, we return a 400 status code with an error message. Conversely, if the input is valid, we respond with a 200 status code, confirming that the user data has been received along with the submitted user information. Finally, to utilize our newly defined routes, we will import the user routes into our main server, TS, file and use it under the /API/user endpoint. This modular design effectively organizes our application code, paving the way for easier maintenance and scaling in the future. Next, we will create a directory for our tests to ensure the quality of our application's backend. Start by organizing your test files into a newly created folder called Tests. Within this folder, we will set up a file named userRootesTest, where we will write our tests for the user routes we established earlier. Now let's implement a simple test suite using Jest and Supertest. In this test file, we first import the required modules including Express, Supertest, and our user routes. We initialize an Express application and integrate the user routes with it. In our test suite, we will define two tests. The first checks whether successful post request to the /API/user endpoint returns a 200 status code and the expected success message with the user data. The second test ensures that if the required fields, name or email, are missing from the request, the server appropriately responds with a 400 error status and an informative message. This structured approach allows us to validate our API endpoints and verify that they handle data as intended, providing a safety net during development. Finally, we can run our tests to confirm everything functions as expected. Congratulations, you've successfully configured a TypeScript backend application using Express.js. We've covered how to set up a TypeScript environment, create a simple server, define routes, manage middlewares, handle errors, structure your code effectively, and set up testing. This foundational knowledge is crucial as you continue building your applications. Remember, crafting efficient and maintainable code will save you time and effort in the long run. Now that you've grasped these concepts, you're well equipped to build full-stack applications while utilizing the power of TypeScript and Express. Happy coding, and I can't wait to see the amazing apps you'll. Now let's take a look at how union types work in TypeScript by examining a function that formats values. In this example, the format value function is defined to accept a parameter called value, which can either be a string or a number. This flexibility is a core benefit of TypeScript, allowing functions to handle multiple types gracefully. Inside the format value function, we employ the typeof operator to determine the type of the input. If the input is a string, we transform it to uppercase using the toUpperCase method. Conversely, if the input is a number, we format it to 2 decimal places utilizing the toFixed method. This approach not only accommodates different input types, but also ensures that the output is consistently formatted based on the type of value provided. Lastly, to demonstrate the function's capabilities, we invoke it with both a number and a string. When passing a number, the function returns a string formatted with 2 decimal places, while passing a string results in its uppercase representation. This illustrates the power of union types in TypeScript, enabling developers to build more flexible and type-safe functions. Next, we will explore the concept of intersection types, which allows us to combine multiple types into one robust type definition. In this example, we begin by defining 2 interfaces, user and admin. The user interface contains 2 properties, name and email, both of which are strings, while the admin interface has a single property, role, also defined as a string. Now let's implement an intersection type called adminUser by using the AND operator. This new type mandates that an object must conform to both the user and admin interfaces, meaning it must include all properties from both. This is particularly useful for ensuring that an object has the required characteristics of both a regular user and an admin. When we create an object of type adminUser, we instantiate it with values for each of the properties defined in the user and admin interfaces. In this case, our admin object is created with a name, email, and role, ensuring that all properties are appropriately set. The resulting structure guarantees type safety, providing confidence that our objects will adhere to the expected shapes within the application. Now let's see how we can implement a generic function that enhances code reusability while maintaining type safety. This function, named createArray, takes 2 parameters, a number representing the desired length of the array and a value of a generic type t. The beauty of generics lies in their ability to allow the developer to specify the type when invoking the function, enabling the creation of arrays that can hold different data types, such as numbers or strings. For instance, in our example, we can create an array of numbers by calling createArray with a length of 3 and a value of 7, resulting in an array filled with the value 7 3 times. Similarly, we can create an array of strings by specifying the string hello and requesting a length of 2. When we call this function, TypeScript ensures that the types we provide match those specified in the function's signature, offering robust type safety. This feature enhances our applications by allowing us to avoid writing multiple functions for different types of arrays, thus improving code maintainability and reducing duplication. By using generics, we can create more versatile functions adaptable to various scenarios in our TypeScript applications. Now let's implement a function that we want to test, specifically a simple function that takes a number as input and returns its double. The sample function is declared as an arrow function, which allows us to write concise and clean code. It takes a single parameter, num, which is of type number, ensuring type safety. Inside the function, we simply return the product of num multiplied by 2. This straightforward functionality helps demonstrate how we can establish a base for writing tests. Next, we will write a suite of tests for sample function using jest. Here, we import the function we will be testing to maintain a clear structure. We define a test suite using jest's describe method, which groups related tests together and makes it easier to organize our testing logic. Inside this suite, we create individual test cases with it blocks that specify what we expect from the function. Our tests check various input values, ensuring that the function returns the correct double for a positive number, a negative number, and 0. By asserting expected results with jest's expect function, we validate that our implementation behaves as intended, keeping our code reliable and functional. Now let's see how we can implement a function to fetch data from an API using Axios. In this code, we begin by importing the Axios library, which is a promise-based HTTP client for browsers and Node.js. The fetch data function is then defined as an asynchronous function that takes a URL as a parameter and returns a promise that resolves with the response data. This allows us to handle the asynchronous nature of the data fetching process cleanly by using the async await syntax. When the function is executed, it awaits the response from the Axios get method called with the provided URL, extracting the data from the response object before returning it. Next, we will write a test for this fetch data function, leveraging jest's mocking capabilities to simulate the behavior of the Axios library without making actual network requests. By using jestmock, we can create a mock for the Axios module, allowing us to define how Axios should behave during the test. Specifically, we will configure it to return mock data when the get method is called. This approach enables us to verify that the fetch data function correctly handles the response it receives from Axios, all while ensuring our tests run efficiently and quickly, without the overhead of real HTTP requests. Now let's implement the dotenv package to manage our environment variables effectively. First, we need to install the dotenv package as a development dependency. This package allows us to load environment variables from an env file into our application. Next, we create an env file at the root of our project, where we define our sensitive configurations, such as API keys. For example, we can set our API key variable to store our key securely, preventing it from being hard-coded in the codebase and thus reducing the risk of accidental exposure. Now let's take a look at how to access these environment variables in our TypeScript files. We begin by importing the dotenv module and calling the config function to load the variables. By doing so, the processenv object becomes populated with our defined variables, allowing us to use them throughout our application. For instance, we can retrieve our API key by referencing process.env API key. This practice ensures that sensitive information remains hidden from the source code, while also affording flexibility for different environments such as development, testing, and production. Using environment variables helps maintain clean and secure code. Now let's see how we can integrate Husky to automate our testing process using Git hooks. To begin, we will install Husky as a development dependency in our project, which will allow us to create hooks that can trigger actions at different points in the Git workflow. This is essential for maintaining code quality because it can ensure that our tests run automatically before any commits are made. After the installation, we need to configure Husky by adding a configuration section in our package.json file. This involves setting up a pre-commit hook that invokes the test command. Now, whenever you attempt to make a commit, Husky will automatically trigger our test suite to run first. If any tests fail during this process, the commit operation will be aborted, preventing faulty code from being committed to the codebase. This step is crucial in fostering a healthy testing culture within the development team, as it not only saves time, but also ensures that new code does not introduce new bugs, maintaining the integrity of our application and streamlining our development workflow. To wrap up, we've explored some advanced TypeScript features like union types, intersection types, and generics, which empower you to write more flexible and reusable code. Additionally, we delved into testing strategies that can help you maintain a clean separation between production and test code using Jest. We also discussed the importance of mocking, using environment variables, and automating tests to ensure consistency in your development process. Arming yourself with these advanced features and strategies doesn't just enhance your TypeScript skills, it allows you to build robust applications while maintaining best practices throughout your workflow. Keep experimenting with these techniques as you develop your projects. The best way to master these skills is through practice and applying them in real-world scenarios. Now let's check the version of Node.js installed on your machine using the command node-v. This command will show the current version of Node.js, confirming that the installation was successful. It's important to ensure you have a compatible version, as TypeScript relies on Node.js for runtime execution. Following that, we'll verify the version of npm, the Node package manager, with npm-v. This step is essential because npm will be our tool for managing project dependencies, including installing TypeScript itself. Once we confirm that npm is installed, we can confidently move forward with the setup process, knowing we have the right environment for developing our TypeScript project. These steps ensure that our development setup is solid before diving into creating our TypeScript project and utilizing its powerful features. Next, we will initialize our npm project. By running the command npm init-y, we automatically agree to the default settings, creating a vital package, JSON file that contains metadata about our project. This file will help npm manage our dependencies efficiently. Now let's see how we can install TypeScript for our project. By executing npm install savedev TypeScript, we ensure that TypeScript is added as a development dependency. This means it will be used during development but won't be included in our production builds, keeping our production environment clean. Finally, we will check if TypeScript is successfully set up by using the command npx-tscv. Here, npx serves as a package runner, allowing us to execute commands from the local node modules. If you see a version number, it confirms that TypeScript is installed correctly, signaling that you're ready to dive deeper into TypeScript development. Next, we will create a TypeScript configuration file by running the command npx-tscinit. This command generates a tsconfig JSON file, which serves as the cornerstone for any TypeScript project. Inside the configuration file, we'll define various compiler options that tailor the TypeScript compiler's behavior to fit our project's needs. Now let's see how we can configure some essential options. We will set the target to ease next, allowing us to utilize the latest ECMAScript features during compilation. The module option is crucial for defining the module system, and we typically set this to CommonJS as it is widely used in Node.js applications. Enabling the strict option is also highly recommended, as it activates all strict type checking options to enhance type safety. Finally, by adding ease module interop and setting it to true, we facilitate default imports from modules that do not have a default export, making it easier to work with existing JavaScript libraries. Together, these settings streamline the development process and ensure your TypeScript project is robust and maintainable. Now let's take a look at how to create the initial structure for our TypeScript project. First, we need to create a directory called src, which will serve as the main folder for our source files. This organization helps keep our project tidy, separating the source code from any compiled files. Next, we will create our first TypeScript file, index.ts, within the src folder. This file will house our TypeScript code. Now let's implement a simple function called greet, which takes a string parameter name and returns a greeting message. This is a fundamental type-safe example of how TypeScript handles function definitions with specific parameter types, providing clarity and reducing potential runtime errors. After defining the function, we will then use console.log to invoke it with the argument TypeScript student, showcasing how TypeScript translates our code to JavaScript seamlessly. Finally, we will compile this TypeScript code into JavaScript using the npx-tsc command. This step is crucial as it converts our TypeScript files into JavaScript, allowing them to run in any JavaScript environment. By compiling, we see firsthand how TypeScript improves our coding experience and provides immediate feedback through type checking. Now let's implement a key configuration option for our TypeScript project. In the tsconfig JSON file, we will specify the outDia property within the compiler options. Setting outDia to dist directs the TypeScript compiler to place all compiled JavaScript files into a separate dist folder after the compilation process. This practice aids in keeping our project organized by distinguishing between source files located in the src directory and the generated files in the dist folder. Organizing files in this manner enhances clarity within the project structure, making it easier to navigate and maintain. Once you have made this adjustment, it's essential to rerun the TypeScript compiler using the npx_tsc command. Upon successful execution, you will see the compiled JavaScript files migrated to the dist folder. This separation not only streamlines project organization, but also minimizes the risk of accidentally modifying generated files, thus fostering a more efficient development workflow. Now let's see how we can enhance our greet function to incorporate TypeScript's advanced type-checking capabilities. In this updated version, the function accepts a parameter called name, which can either be a string or null. This is a significant improvement as it allows for more robust handling of input values. The first thing we do in the function is check if name is null. If it is, we throw an error with a descriptive message stating that name cannot be null. This serves as a safeguard, preventing potential runtime errors when the function is called with unexpected values. By catching this error at the compile time level, TypeScript helps ensure better code reliability. If name is not null, the function proceeds to return a greeting message that includes the provided name. This simple yet effective approach demonstrates how TypeScript's type system can be leveraged to enforce stricter definitions for function parameters, ultimately leading to fewer bugs and more predictable code behavior. This is a key advantage of using TypeScript, as it allows developers to express intentions clearly while still maintaining flexibility in their function implementations. Next, we are going to introduce testing capabilities into our TypeScript project using Jest, a widely used testing framework. To do this, we will first install Jest along with its TypeScript transformer, tsJest, and the type definitions for Jest using npm. This step is crucial as it allows us to write tests for our TypeScript code and ensures that the tests can understand TypeScript syntax. Now let's create a basic configuration file for Jest. By adding a Jest config.js file, we specify that Jest should use tsJest to process our TypeScript files. This configuration also sets the testing environment to Node.js, which is necessary since our TypeScript project runs on it. Setting up this configuration will facilitate a smooth testing process, allowing us to focus more on writing tests rather than configuring the testing framework. With Jest integrated, we establish a robust testing foundation that helps maintain our code quality through constant validation of our implementations. This step is essential to ensure that all features we develop function as expected while promoting a reliable development lifecycle. Now let's write a test for our greet function. First, we create a new directory named tests to store our test files, promoting organization in our project. Inside this directory, we will create a test file called greet_test_ts. In this file, we will utilize Jest's describe function to group our tests related to the greet function. Next, we will define specific test cases using the it function. The first test case checks if the greet function correctly returns a greeting message when a valid name is provided. By using expect, we assert that calling greet TypeScript returns the expected message, hello TypeScript. For our second test case, we will verify that the function handles erroneous input appropriately. Here, we will test if passing null, as the name throws an error with the message, name cannot be null. This approach demonstrates how to ensure both the expected behavior and error handling of our function through structured testing, thus enhancing code reliability and robustness. Now let's see how we can execute our tests using Jest. To run the tests we've written for our greet function, we'll use the command npx_jest. This command leverages npx, a tool that allows us to run packages from the local node modules without having to install them globally. By executing this command, Jest will scan through our project to find any test files it recognizes, specifically those that follow the naming conventions we've set. Once Jest identifies the test files, it will run each test and display the results right in your terminal. You'll see output indicating whether each test passed or failed, along with any error messages for those that didn't. This feedback loop is crucial because it helps you ensure your code works as intended, providing confidence in the functionality of your applications. Moreover, this practice encourages you to write tests consistently for new features, instilling a habit that enhances code reliability and maintainability. As you progress in your development journey, remember that automated testing through systems like Jest is an invaluable tool in maintaining code quality. In this video, you've learned how to set up a TypeScript project from scratch, including installing necessary tools, creating project structure, writing TypeScript code, and even integrating testing with Jest. Having a well-structured setup like this allows you to build scalable and maintainable applications effectively. As you move forward, continue to explore TypeScript's advanced features, libraries, and best practices for even better development experiences. Don't forget, the community around TypeScript is vast and filled with resources, so if you ever hit a snag, don't hesitate to reach out and seek help. Happy coding, and see you in the next. Now let's take a look at a simple example of type checking in JavaScript using the typeof operator, which helps us determine the type of a variable at runtime. In this snippet, we first declare a variable and assign it a string value. By using console.log with typeof, we can observe that the type of the variable is correctly identified as a string. Next, we reassign the variable with an integer value and log its type again. As expected, the output confirms that it is now a number. Then we change the variable's value to a Boolean and log its type one more time, showing that the flexibility of JavaScript allows variables to change types dynamically. However, it's crucial to understand the limitations of this approach. For example, when we use typeof on an array, it returns object, which is not particularly informative. This highlights the need for more robust type-checking measures when dealing with complex types, setting the stage for exploring further techniques that TypeScript can offer. Now let's take a look at how we can utilize the instanceof operator to accurately check object types in JavaScript. In our example, we define a person class with a constructor that accepts a name parameter. This is a straightforward way to create custom objects. When we instantiate the class by creating a person object with the name Alice, we leverage the instanceof operator to check if person is an instance of the person class. This check returns true, confirming that the object is indeed created from our defined constructor. Additionally, we demonstrate the versatility of the instanceof operator by validating other built-in types. For instance, checking an empty array with instanceof array returns true, and the same goes for an empty object with instanceof object. This mechanism provides a more precise way of determining the type of an object compared to using the typeof operator, especially when dealing with custom types. However, it's important to note that complex inheritance scenarios can still introduce some confusion in type checking with instanceof. Hence, understanding these nuances is crucial when working with JavaScript and custom types. Now let's see how TypeScript enables us to define functions that accommodate multiple input types using union types. In our logid function, we specify that the parameter id can either be a number or a string. This flexibility allows the function to handle various types of input while ensuring type safety. TypeScript's compiler checks for type consistency before the code runs, preventing errors that might arise from passing incompatible types. When we call logid with both a numeric ID and a string ID, it correctly logs the provided value, showcasing TypeScript's ability to manage different data types smoothly. Next, we'll take a look at TypeScript's powerful type guards, which let us create functions that narrow down the type of a variable based on certain conditions. In the isString function, we check if the input value is a string. By asserting the type in our conditional statement, we allow TypeScript to deduce the type of the variable sample as a string within the if block. This capability allows us to safely call string-specific methods, such as toUpperCase, without encountering type errors, thereby enhancing our code's reliability by safeguarding against incorrect assumptions about variable types. Now let's take a look at how TypeScript can enhance our type-checking capabilities when working with the document object model DOM. In this example, we assert a variable, input element, by using the as keyword to let TypeScript know that we are specifically dealing with an HTML input element. This assertion allows us to safely access properties and methods unique to input elements, such as the value property, without fear of type-related errors. By assigning a string to input element value, we demonstrate how this type assertion effectively communicates our intent to the TypeScript compiler, enforcing stricter checks during development. Next, we will write a generic function called identity, which is a powerful feature of TypeScript that allows us to create flexible and reusable components. This function takes a generic type parameter t, acting as a placeholder for any data type provided during invocation. This design promotes strong typing while enabling us to use the function with various data types, thereby enhancing code reusability. when we call identity with the argument hello generics. TypeScript understands that result will hold a value of type string, maintaining type safety throughout our code. Now let's see how we can utilize enums in TypeScript to enhance our code clarity and type checking capabilities. Enums are a powerful feature that allows us to define a set of named constants, which can significantly improve code readability. In our example, we define an enum named color with 3 possible values: red, green, and blue. This clearly defines our color options in a way that is easy to understand and prevents the use of arbitrary values. Next, we declare a variable named favorite color and assign it a value from the color enum. In this case, favorite color is set to color green. This usage not only makes it evident that favorite color can only be one of the defined enum values, but it also avoids common errors associated with using raw strings or numbers to represent these colors. When we log favorite color, we see the output as 1, which indicates the index of green in the enum. This is a clear demonstration of how enums can lead to more maintainable and less error-prone code by making the relationships and possible values explicit. Now let's take a look at tuples, which allow us to create an array that can contain elements of fixed types at specific positions. In our example, we declare a tuple named tuple that contains a string followed by a number. This structure helps ensure type integrity, where the first element must always be a string and the second element a number. When we log tuple, we see that it outputs the expected array format, thus confirming that our tuple is correctly enforcing its types. By leveraging tuples, we can create more organized and predictable data structures that enhance our type-checking strategy within TypeScript. In conclusion, type-checking is an essential aspect of robust software development, especially in loosely typed languages like JavaScript. By employing techniques such as type-off, instanceoff, type guards, assertions, and TypeScript's strong static type checking, we can significantly reduce the number of runtime errors and improve our code's readability and maintainability. The transition from JavaScript to TypeScript may seem daunting at first, but once you embrace its capabilities, the advantages will become evident. Having set up your TypeScript environment, integrated testing, and understood the core concepts of type checking, you're well on your way to becoming proficient at maintaining safer, more reliable code. So remember, each time you write a line of code, think about the types you are dealing with, and don't hesitate to leverage the power of TypeScript to enhance your JavaScript experience. Happy. Now that we have Node.js installed and our project initialized, let's verify that everything is in order. We'll begin by checking the versions of Node.js and npm in our terminal. This step is essential to ensure that our development environment is set up correctly before we proceed. Verifying the installations will give us confidence that the tools we need to build our full-stack application are ready to go. Next, we will create a new directory for our project, which will serve as the foundation for our full-stack application, and then initialize an npm project within that directory. This process involves generating a package, JSON, file through the npm init command, which automatically provides us with a default configuration. This file is critical as it maintains all the dependencies and scripts necessary for our project, allowing us to easily manage them as we build our application. Now let's implement TypeScript into our project. We'll begin by installing TypeScript as a development dependency using npm, along with the TypeScript node runner and Node.js types to ensure a smooth development experience. This command adds essential tools that will help us develop our application in TypeScript while seamlessly compiling our code for execution. Next, we will generate a TypeScript configuration file, tsconfig.json, automatically. This file is crucial as it defines how TypeScript should compile our code. We want to ensure that our setup targets ECMAScript 2020 and specifies that we will be using common JS modules, which are commonly utilized in Node.js applications. The configuration will direct the compiler on where to place the compiled files and where to find the source TypeScript files. Setting the strict option to true is particularly beneficial, as it enhances type checking, leading to more reliable and maintainable code. With our TypeScript configuration in place, we can confidently proceed with coding, knowing that our setup is optimized for both development and production environments. Now let's create a simple server using Express, a popular framework for building web applications in Node.js. First, we begin by importing the Express module, which provides a robust set of features for web and mobile applications. Next, we create an instance of the Express application, allowing us to set up our server and define various routes to handle incoming requests. We specify a constant part to define the part on which our server will listen. This value can come from an environment variable, making our server flexible in different environments, or it will default to 3000 if no variable is set. Now let's define a GET route for the route URL. This route uses the app-get method to specify how the server should respond when a request is made to the base route by sending back a greeting message. Finally, we employ the applisten method, which instructs our server to listen for incoming connections on the defined part. This method also includes a console log to confirm that the server is running successfully. With this basic setup, we can check our Express server by visiting http://localhost 3000 in a web browser, where we expect to see the greeting message displayed. Now let's implement a simple React application to serve as the front end of our full-stack application. First, we navigate into the client directory and initialize a new React project configured with TypeScript. This setup allows us to leverage TypeScript's type-checking capabilities, ensuring a robust code structure right from the start. Next, we turn our attention to the app.tsx file where we define our main React component. In this component, we establish a state variable called message using the useState hook, which will hold the data retrieved from our Express server. To fetch this data, we utilize the useEffect hook that runs when the component mounts. Here we define an asynchronous function, fetchData, that sends a GET request to our server at http://localhost 3000. When the data is received, we update the message state with the server's response. Finally, we render a simple UI that displays a title and the message fetched from the server. When you run the React app, it will show the dynamic message, demonstrating real-time communication with the backend service we previously set up. Now that we've established our Express server, let's implement CORS middleware to handle cross-origin requests between our client and server applications. First, we need to install the CORS package along with its type definitions. This middleware is crucial as it allows your server to specify which domains are permitted to access its resources, thereby enhancing security while enabling your React application to interact with it without running into CORS-related issues. Next, we will update our server TS file to incorporate CORS into our server setup. By importing the CORS library and invoking it with app use CORS, we effectively enable CORS for all routes in our Express application. This is an essential step in ensuring that when both the client and server are running, they can communicate smoothly. With this CORS configuration in place, your React app can successfully send requests to your server hosted at http://localhost 3000. This seamless interaction allows you to leverage the full-stack capabilities of your application effectively, ensuring a responsive and integrated user experience. Now let's enhance our application by introducing a shared directory for common interfaces and types. Next, we will create a directory named shared, positioned at the same level as both the client and server directories. This structure allows us to maintain a clear separation while providing a dedicated space for types that can be used throughout the application. In the shared folder, we will define a TypeScript interface for a user. This interface will include properties such as ID, name, and email, ensuring that both the server and client can rely on a uniform user model. By doing this, we foster consistency across both ends of our application and leverage TypeScript's static typing features, which aid in catching potential errors during development. Now let's implement this user interface in our TypeScript file called user.ts. Once completed, you will be able to import and utilize this interface in both your Express server and React application. This practice not only streamlines our code, but also reinforces TypeScript's strong typing system, enhancing the maintainability and reliability of our full-stack project. Finally, let's talk about managing application growth. As our application scales, managing dependencies and using a proper build system is crucial. Utilizing tools like Webpack or Parcel for the client-side build process can streamline this effort. These tools handle JavaScript bundling and can manage assets more efficiently than manually importing and linking files. You can integrate these build tools into your React project, simplifying the deployment process. To deploy your full-stack application, consider using platforms like Heroku for the server-side application and Vercel or Netlify for the client-side. Prepare your code for production by building the React application using npm run build, which optimizes your application for deployment. In summary, starting from a multi-tier architecture with shared types, using TypeScript for robust type checking, and setting up server and client interactions seamlessly creates a solid foundation for any full-stack application targeting Node, JS, and the browser. Now you're equipped with the knowledge to create your very own full-stack TypeScript application. Getting started with TypeScript is an exciting journey. You'll find that integrating TypeScript into your projects can offer numerous advantages, enhancing your coding experience and improving your application's robustness. In this session, we will dive into the intricacies of project setup for TypeScript, covering the essential components and configurations required to create a solid foundation for your applications. So far, we learned how to set up a full-stack TypeScript project targeting Node.js in the browser, created a basic Express server and a React application, and shared types for consistency. Now, we will talk about how to streamline the process of integrating TypeScript into various projects and ensure your setup is both efficient and scalable. Now let's take a look at how to initialize our TypeScript project using npm. The first command we will run is npm init. This command initializes a new project by creating a package, JSON file that will hold important metadata about our project, such as its dependencies, scripts, and configurations. The Y flag ensures that default values are automatically filled in without prompting us for additional input, streamlining the setup process significantly. Next, we will install TypeScript as a development dependency. To do this, we will execute the command npm install TypeScript save dev. This command adds TypeScript to our project, allowing us to utilize its compiler and take advantage of its features like static typing and advanced tooling. The save dev flag indicates that TypeScript is needed only during our development phase and won't be part of the final production build, helping us manage dependencies effectively. With both commands executed, we now have a solid foundation for building our TypeScript project, ready to enhance our development experience. Next, we will create a TypeScript configuration file to instruct the TypeScript compiler on how to handle our codebase. This can be accomplished by running the command npx-tscinit, which generates a tsconfig JSON file with default settings tailored for your project. Now let's take a look at the key options within the tsconfig JSON. The compile options section defines settings that control the compilation process. For instance, the target option specifies that TypeScript should compile our code to ECMAScript 6, which is widely supported and offers many modern features. The module option is set to common, making it suitable for environments like Node.js where common JS module syntax is prevalent. Enabling the strict option activates strict type checking, which assists in identifying potential issues early on. Additionally, the ease module interop option enhances interoperability between common JS and ES modules, while skiplibcheck can save time by bypassing type checking for declaration files. The FOSS consistent casing in file names option ensures that file names are treated consistently across different operating systems. Finally, by using the include and exclude fields, we can specify which files TypeScript should compile or ignore. This keeps the project organized, allowing for a clearer distinction between source files and test or configuration files. Now that we have our folder structure ready, let's create a sample TypeScript file to test our setup. We will implement a simple function named greet, which takes a single parameter, name, typed as a string. The function returns a greeting message that incorporates the provided name. This showcases TypeScript's strong typing feature, ensuring that the function receives the correct data type, thereby reducing potential runtime errors. Next, we will proceed to log the output of the greet function to the console, passing the string TypeScript enthusiast as an argument. This interaction not only demonstrates the function's capability to generate personalized messages, but also allows us to verify that our TypeScript code compiles correctly into JavaScript. Now let's compile this TypeScript file using the TypeScript compiler. By executing the compilation command, we will generate a corresponding JavaScript file in the dist folder. This output file can be run with Node.js, enabling us to execute our TypeScript code in a JavaScript environment and see the greeting displayed in the console, confirming that our setup and code are functioning as intended. Now let's see how we can enable watch mode in our TypeScript project. By running the TypeScript compiler with the watch flag, we allow the compiler to automatically monitor our TypeScript files for any changes. This means anytime we modify a file, such as index.ts, TypeScript will immediately recompile our code into JavaScript. This feature is incredibly beneficial during development, as it provides instant feedback and eliminates the need for manual compilation, allowing us to focus more on writing code rather than managing the build process. Next, as our project grows, managing external libraries will become essential. We can implement this by using the npm install command to bring in libraries like Express and React, which are commonly used in web applications. This command installs the specified packages and updates our project's package.json file, ensuring that we have all necessary dependencies documented. Keeping our package dependencies organized is crucial for maintaining consistency across different environments and avoiding potential conflicts as our project evolves. Next, we will implement testing for our TypeScript application using Jest. First, we use the command to install Jest and its necessary dependencies. TS-Jest helps Jest integrate with TypeScript, while @types-Jest provides TypeScript type definitions. This setup is crucial for a seamless testing experience in our TypeScript environment. Now let's configure Jest to recognize TypeScript files. By running the configuration command, we generate a Jest config.js file which we can customize. In the configuration, we specify TS-Jest as the preset and define the testing environment as Node.js. This setup allows Jest to understand how to handle TypeScript files during execution. Once the configuration is complete, we can create a test file in a designated tests directory to validate our functions. Here, we'll import the greet function from our source code and write a simple test case. This test checks whether the output of the greet function, when provided with a specific input, matches the expected greeting message. Finally, running the Jest command allows us to execute our tests, and we will receive feedback on whether the tests passed successfully, ensuring that our code functions as intended. Now let's take a look at the recommended folder structure for your TypeScript project. Organizing your code effectively is crucial as it enhances maintainability and clarity as your project grows. In this structure, we have a dist folder, which is designated for your compiled JavaScript files that the TypeScript compiler generates. This keeps your original TypeScript code separate from the output files. Next, we maintain a Node Modules directory, which houses all of your project's dependencies, ensuring that everything needed is bundled neatly together. The src folder contains your source TypeScript files, such as index.ts, where you will write your application logic. For testing purposes, a dedicated tests directory organizes all your test files, making it easy to locate and run tests separately from your core application code. Finally, the package.json file is essential because it includes metadata and manages your dependencies, while the tsconfig.json file defines compiler options. This structured approach not only simplifies navigation, but also fosters a collaborative coding environment by adhering to consistent naming conventions and documentation practices. Welcome to today's lesson on configuring TypeScript settings. In this session, we'll dive into the intricacies of TypeScript's configuration options, which play a vital role in optimizing your development workflow and enhancing the quality of your code. So far, we learned how to set up a TypeScript project using npm, which includes initializing the project, installing TypeScript, and creating a configuration file. We organized our project structure by creating src and dist folders and wrote our first TypeScript function. Additionally, we explored running TypeScript in watch mode for efficient development and installed Jest for testing our TypeScript applications. Finally, we discussed best practices for project organization and documentation to enhance collaboration and maintainability. Now we will cover the various settings available in the TypeScript configuration file, tsconfig.json, and understand how to leverage them to tailor TypeScript to our specific development needs. Now let's take a look at the configuration settings defined in the tsconfig.json file. This file is essential for controlling how TypeScript compiles your code, and it contains a range of options under the Compile Options section. For instance, we set the target to ease6, which allows us to leverage modern JavaScript features while maintaining compatibility across different environments. The module option is set to Commons, which is particularly suitable for Node.js applications, enabling modular code management. Furthermore, the strict option, configured to true, activates a series of strict type-checking features that enhance the safety of our code by catching potential issues early. We also enable ease module interop, facilitating the seamless import of common JS modules. The skiplib check setting skips type checks on declaration files, helping to speed up compilation, especially useful in larger projects. Additionally, the include array ensures that TypeScript compiles all files in the src directory and its subdirectories, while the exclude option clarifies that we want to ignore node modules and test files ending with spec.ts, focusing on our relevant source code. This structure provides an efficient setup for our TypeScript project. Then there's the strict option, which elevates TypeScript's type-checking capabilities. When set to true, this option activates a series of other flags like no implicit any, strict null checks, etc. that enhance type safety. If you prefer more relaxed type checking, you can set this to false. However, doing so might lead to overlooking potential errors in your code, which could lead to bugs in production. The ease module interop ensures that you can import CommonJS modules seamlessly, which is particularly useful when you rely on various libraries in your application. By default, ES modules and CommonJS can have issues when imported together without proper interoperability. Enabling this option helps mitigate such issues. Another point of interest is the skiplibcheck option. By setting this to true, TypeScript skips type checking of all declaration files, which can speed up the compilation process. It's an excellent option for larger projects where you generally trust the types defined in third-party libraries. Lastly, consistent casing in file names ensures that file names are treated with consistent casing. This is crucial in environments like Linux, where the file system is case-sensitive. It protects your project from errors related to case mismatches. Next, let's discuss the include and exclude arrays, which help TypeScript determine which files to compile and which ones to ignore. By default, TypeScript checks all TS and TSX files in your project. However, you might want to include or exclude certain files to avoid compiling unnecessary code. In the example, we see that include is set to src/**/, meaning all TypeScript files inside the src directory and its subdirectories will be included in the compilation process. The double asterisks denote a recursive search through the directory tree. On the contrary, the exclude option will ignore files we don't want to compile. For example, we can exclude the node modules directory, as we don't need to compile the third-party libraries and any test files matching the pattern /*spec ts. Now let's see how we can enable stricter type checking features in our TypeScript configuration by adding two essential options. First, we'll implement the no implicit any setting, which requires all parameters and variables to have explicitly defined types. By doing this, we ensure that our code adheres to a higher standard of type safety, reducing the likelihood of runtime errors and enhancing overall code quality. Next, we can activate strict null checks. This option mandates that we explicitly handle null and undefined values throughout our codebase. With this setting enabled, TypeScript will notify us of potential issues whenever we attempt to utilize these values without appropriate checks, thus preventing runtime exceptions related to null dereferencing. Both of these configurations promote a more stable development environment, allowing us to catch errors early during the coding process. By incorporating these options into our tsconfig JSON, we are moving towards writing clearer, more maintainable TypeScript code that is easier to debug and less prone to failure. Now let's implement the outDia and rootDia options in our tsconfig JSON file to improve our project organization. The outDia option specifies where TypeScript should place the compiled JavaScript files, ensuring a clear separation from your source code. In this case, we set it to a dist folder, which is a common practice to keep build artifacts organized. On the other hand, rootDia defines the directory that contains your TypeScript source files, set as src here. This structure indicates to TypeScript where to look for the original TypeScript files to compile. By defining these paths, we establish a tidy project layout that not only aids in development, but also scales well as your project grows. Additionally, we can enhance our debugging process by introducing the source map option. By enabling this, TypeScript will generate source map files alongside the compiled code. These files are crucial when debugging, as they allow you to trace back from the JavaScript running in production to your original TypeScript code, making it easier to identify and rectify issues. This setup ultimately contributes to a smoother development experience and greater maintainability of your project. Now let's take a look at how we can enhance our TypeScript configuration by adjusting the module resolution and implementing project references. In the code, we first set the module resolution to Node. This mode is suited for modern projects as it mimics the way Node.js handles module imports, which is particularly useful when working with various libraries and ensuring compatibility. Next, we introduce project references, which are a powerful feature for organizing larger projects. By adding the composite option, we signal to TypeScript that this project is part of a larger workspace and can be built independently. The outDia directive specifies where the compiled files should be placed, helping to keep our project structure clean and organized. The references array follows, allowing us to point TypeScript to other projects in the workspace. Each entry provides the path to a dependent project, ensuring that TypeScript builds them in the correct order. These configurations together not only optimize compile times, but also promote better project organization and maintainability, especially significant in team environments or large code bases. Now let's implement the incremental option in our tsconfig JSON file to enhance our build process. By enabling this setting and setting it to true, we allow TypeScript to keep track of changes to our source files and create a tsbuildinfo file. This file stores information about the previous compilation, enabling faster builds by skipping recompilation of unchanged files. As your project grows, this can significantly reduce build times, making the development experience smoother and more efficient. Next, we will write the code for the experimental decorators option. By setting this option to true, we allow ourselves to utilize decorators within our TypeScript code. Decorators are a powerful feature, especially useful in frameworks like Angular, where they can simplify the way we annotate and manipulate classes or methods. However, it's essential to keep in mind that since decorators are still considered experimental, their implementation may change in future TypeScript versions. Therefore, consulting the official TypeScript documentation is recommended when working with these features. Together, these options enhance type and build efficiency in TypeScript projects, allowing for a more robust development process. Now let's see how we can enhance our TypeScript project by adding type definitions for third-party libraries. For instance, when working with the Lodash library, which may not have built-in TypeScript definitions, we utilize the @types package to remedy this situation. The command npm install savedev @types/lodash does exactly that. By running this command, we install the type definitions specifically for Lodash, allowing TypeScript to recognize the types used by the library. This integration improves type safety within our project, enabling TypeScript to provide accurate type checking. As a result, we gain various benefits such as cleaner code and enhanced autocomplete options while coding, making our development experience more efficient and less error-prone. By incorporating these type definitions, we not only adhere to best practices, but also ensure that our interactions with external libraries remain robust and reliable, paving the way for more maintainable code in our TypeScript applications. In conclusion, configuring TypeScript settings through tsconfig JSON plays a crucial role in how effectively you can develop your applications. We started by reviewing the basic settings, moved on to stricter type checking options, and explored advanced project organization tactics. These configurations empower you to tailor TypeScript to fit your unique development needs while enhancing code quality and maintainability. With the right settings, your code can become more consistent and easier to work with, setting the groundwork for successful projects. So as you progress in your TypeScript journey, continuously refer to your tsconfig JSON, explore different options, and experiment with settings that could improve your workflow. Remember, the beauty of TypeScript lies in its flexibility and power to transform your coding experience. Keep practicing, keep coding, and let TypeScript guide you towards building robust and scalable applications. Now let's take a look at how we can define a module in TypeScript that showcases both type definitions and functional exports. In our example, we begin by declaring a type called operation that restricts values to either add or subtract. This ensures that any operation passed into our functions is type safe, reducing the risk of runtime errors associated with invalid operations. Next, we implement the calculate function, which takes two numbers and an operation of type operation. Inside the function, we use a switch statement to examine the operation passed by the user. If the operation is add, the function returns the sum of the two numbers. If it's subtract, it returns their difference. This structure not only organizes our code, but also illustrates how TypeScript's strong typing can enhance clarity and reliability. Lastly, we ensure robust error handling by throwing an exception if an invalid operation is provided. By exporting both the operation type and the calculate function, we make them available for import in other parts of our application, promoting modularity and reusability in our TypeScript projects. Now let's implement the following code that demonstrates how to utilize our calculate function from the math.ts module in another file called app.ts. First, we begin by importing the calculate function and the operation type that we previously defined, which allows us to specify the types of operations we can perform, such as addition or subtraction. By invoking the calculate function with specific numbers and an operation, we store the results in resultAdd and resultSubtract. Next, we log these results to the console. The first log statement outputs the result of adding two numbers, displaying it as addition result 8, while the second log shows the result of subtracting the two numbers, resulting in subtraction result 2. This seamless integration between files illustrates the beauty of modular programming in TypeScript, where code reusability and organization are paramount. However, keep in mind potential complications when dealing with various module systems, as proper configurations will help avoid issues while importing and exporting functionalities across your TypeScript projects. Now let's take a look at a simple CommonJS module implementation. In this code, we define an array called users that contains 3 string values, Alice, Bob, and Charlie. Next, we create a function named listUsers, which when called will log the contents of the users array to the console. This structure is quite straightforward and crucial for organizing our code, especially when developing server-side applications. To make the listUsers function accessible from other modules, we use module exports, allowing other files to import and utilize this function. This is a core feature of CommonJS that facilitates modular programming. However, if we attempt to use this CommonJS module in a TypeScript application set up as an ES module, we can encounter issues due to differences in how exports and imports are handled between these two systems. Next, we will explore how to properly configure our TypeScript setup to manage these distinctions and ensure that we can effectively use both module types without any conflicts. This understanding is key to maintaining clean and maintainable code across multiple environments. Now let's take a look at how to install and utilize the Lodash library in our TypeScript project. First, we need to install Lodash using npm, a package manager that simplifies the process of managing libraries and their dependencies. We can do this by running a command in our terminal, ensuring that the library is available for our project. Next, we will import Lodash into our TypeScript file to leverage its powerful utility functions. To demonstrate this, we can create an array of numbers and use the shuffle method from Lodash to randomize the order of the elements within that array. This not only showcases how to import a third-party library, but also highlights the ease of use that comes with TypeScript's compatibility with JavaScript libraries, as long as we properly manage type definitions. Furthermore, should the type definitions for our library not be automatically recognized, we would need to install them separately to enhance type safety and avoid potential runtime errors. This reinforces the importance of understanding how to incorporate external libraries while maintaining the integrity and type-checking features of TypeScript in our development workflows. Now let's implement the following Webpack configuration to bundle our TypeScript application. This configuration begins by requiring the path module from Node.js, which simplifies file and directory path management. Next, we define the module's configuration, starting with the entry point, which indicates the main file of our application. Here specified as src/appts. This tells Webpack where to begin the bundling process. Then we specify the output settings, which determine the name of the bundled file, bundle.js, and its output path, directing it to the dist folder using path resolve. Furthermore, the resolve property is crucial as it defines which file extensions Webpack should consider when resolving modules. Both TS and JS are included here, allowing for seamless integration of TypeScript and JavaScript files. Finally, we include the module section, where we set rules for how to handle different file types. In this case, we target TypeScript files with a regular expression and employ tsloader to compile them. By excluding the node modules directory, we ensure that only our application files are processed. This streamlined approach not only optimizes the bundling process, but also enhances browser compatibility. In conclusion, while working with modules and dependencies in TypeScript can present some challenges due to the differences in module systems like CommonJS and ES modules, understanding how to manage these elements effectively is essential for scalable code architecture. We've covered how to create and use modules, the importance of exporting and importing functionalities, and the implications of working with different module systems. We also explored how to incorporate third-party libraries with proper type definitions and the importance of keeping these dependencies updated. Lastly, we touched on the significance of bundling to optimize your code for production. With a solid grasp of all these concepts, you can significantly enhance your code organization, improve maintainability, and make your TypeScript projects more robust and enjoyable to work on. So get out there, start organizing your modules effectively, and watch your TypeScript projects. You want to get started with TypeScript? Fantastic. The big question is, how do you start? In this session, we'll dive into various project setup techniques that will lay the groundwork for your TypeScript journey. we'll discuss configurations, dependencies, and best practices to establish a smooth workflow and enhance your development experience. So far, we learned about the importance of managing modules and dependencies in TypeScript, including how to configure settings in tsconfig, JSON for project organization. We explored the concepts of importing and exporting code between modules and discussed the differences between CommonJS and ES module systems. Additionally, we covered how to effectively incorporate third-party libraries with type definitions and the significance of keeping dependencies updated. Lastly, we highlighted the role of bundling tools like Webpack to optimize code for production environments. Now, let's talk about practical approaches to setting up a project with TypeScript. Next, we'll initialize our TypeScript project by creating a new package, JSON file, which will serve as the foundation for managing dependencies and settings within our project. To do this, we run the command that initializes a new npm project with default settings, simplifying the configuration process. Now let's see how we can install TypeScript as a development dependency. This step allows us to utilize the TypeScript compiler and its associated tools necessary for transforming our TypeScript code into JavaScript. By using the savedev flag in the installation command, we specify that TypeScript is needed only during development, meaning it won't appear in our production build. Following the installation, we need to create a tsconfig, JSON file, which provides essential configurations for the TypeScript compiler. We can easily generate this file with a command that sets up default options. Now let's take a look at how we can configure our tsconfig, JSON to tailor it to our project's needs, ensuring we set the ECMAScript version to the latest, the module resolver to CommonJS, and define where our source files and output files will reside. Adjusting the strict flag will enhance type safety, ensuring we catch potential issues early in the development process. Now let's see how we can implement a simple Express server using TypeScript. We begin by importing the Express library, which allows us to create a web server with ease. After that, we instantiate an application object by calling Express, which serves as our main server instance. Next, we define a constant port set to 3000. This is the port number on which our server will listen for incoming requests. Now let's define a route for the route URL by using apt-get. This method takes two arguments, the path in this case, and a callback function that gets executed when a request is made to this endpoint. Inside the callback, we send a simple response back to the client that says, "Hello world, this is my Express server with TypeScript." This shows how straightforward it is to respond to web requests with custom messages. Finally, we instruct our server to listen on the specified port using applisten. This method not only starts the server, but also includes a callback function that logs a message to the console indicating that the server is running. With this structure, you can easily expand the server to handle more routes and add additional features as your application grows. Now let's take a look at how to configure the TypeScript settings for our server and client applications by creating two separate tsconfig, JSON files. For the server, we begin by setting target to ease next, ensuring compatibility with the latest JavaScript features. The module is set to commons, which is essential for Node.js applications to facilitate module loading. We define the root dia as the current directory, which indicates where our source files reside, and specify out dia to direct compiled files into a separate dist server directory, keeping our output organized. The strict option is enabled to enforce rigorous type checking, while ease module interrupt allows us to import CommonJS modules easily. Next, we will implement the client-side configuration, which has similar foundational settings but with specific adaptations. We maintain the target as easeNext and switch the module type to easeNext to align with modern web standards. The root dia again points to the current directory, while the output files will be directed to dist client. Additionally, we include the lib option with values DOM and easeNext to provide necessary type definitions that are relevant for web applications, enhancing the functionality and reliability of our client code. Now let's see how we can effectively manage external libraries in our TypeScript project by installing Lodash and its type definitions. To begin, we use npm to install Lodash, a popular utility library that simplifies working with arrays, numbers, objects, strings, etc. This also involves installing its type definitions from the definitely typed repository, which provides us with TypeScript types for Lodash. By doing this, we ensure that our development environment offers IntelliSense support, enabling us to use Lodash functions confidently with proper type checking. Next, we'll modify our tsconfig, JSON file to enhance our type safety when working with JavaScript files. We will enable the Allow.js option, which permits the inclusion of JavaScript files in our TypeScript project. Additionally, we will set the check.js flag to true to enforce type checks in those JavaScript files. This approach allows for a gradual transition from JavaScript to TypeScript, improving type safety incrementally. Finally, we specify the output directory through the out.dia option, directing compiled files to stay organized in a designated folder, maintaining a clean project structure. Now let's dive into integrating testing into our TypeScript project. We'll install Jest, which is a popular testing framework, along with its type definitions, and TS-Jest, a transformer that enables Jest to work seamlessly with TypeScript files. By running the installation command with the savedev flag, we ensure these dependencies are added as development tools, meaning they are only needed during the development phase and not in the production environment. Next, we will set up a dedicated folder for our test files, which will help keep our project organized. Inside this folder, you'll want to create a test suite that includes the tests for your application. By performing tests, you'll be able to validate that your application behaves as expected. Compiling your TypeScript test files will allow you to run them efficiently, ensuring that any changes made to the application do not introduce new errors. This testing process is crucial, as it helps maintain the quality and reliability of your codebase as you scale your project, making your build process not just robust, but also sustainable in the long run. In summary, understanding how to set up a TypeScript project efficiently involves several key elements, including initialization with npm, creating appropriate configuration files, managing dependencies, and setting up distinct configurations for different segments of your application. These foundational practices will lead you on the path toward building scalable and maintainable applications using TypeScript. So gear up, dive into coding, and enjoy the benefits of TypeScript. You want to write a full-stack application targeting Node.js and the browser with shared dependencies. In this lesson, we'll explore how to effectively set up a full-stack TypeScript application that bridges the front-end and back-end, allowing for seamless interaction. This journey combines previous learnings by building on initializing TypeScript projects, managing dependencies, and setting up configurations. So far, we learned about initializing a TypeScript project using npm, creating essential configuration files like tsconfig, JSON, and managing dependencies effectively, including adding third-party libraries and their type definitions. We explored how to set up a basic Express server and the importance of structuring projects with separate configurations for server and client components. Additionally, we discussed the gradual adoption of TypeScript in existing JavaScript codebases and the integration of testing frameworks to ensure code quality. These practices provide a solid foundation for developing and maintaining scalable TypeScript applications. Now we will delve into implementing a full-stack application that encapsulates both server-side and client-side code sharing. Next, we will create a simple Express server to handle requests and serve our front-end files. Start by navigating into the server directory and creating an entry point file named index.ts. In this file, we import the necessary modules such as Express and Path. We initialize the Express application and set a part for our server. To handle JSON payloads, we use Express, JSON, and we serve static files from the client directory with Express static. Now let's implement our API endpoint. We'll define a GET request handler for the path/API/data, which responds with a JSON object containing a welcome message. This simple endpoint exemplifies the principle of RESTful APIs by providing data to the front end. Finally, we call applisten to start the server, and a console log will confirm that our server is running at the specified port, making it easy to access from the browser. This establishes a foundational interaction between the client and server and allows us to expand functionality as needed. Now let's implement the following basic Express application to handle our server-side logic. We start by importing the necessary modules, including Express and TypeScript types for request and response, which provide strong typing for our request and response objects. Next, we initialize an Express application instance and define a port number, 3000 in this case, on which our server will listen for incoming requests. Now let's set up middleware to handle JSON requests using Express, JSON, allowing us to parse incoming request bodies formatted as JSON. Additionally, we set up a static file server serving files from the client directory, enabling the server to deliver front-end assets seamlessly. Next, we define an API endpoint at /API/data, which responds to GET requests. When a client sends a request to this endpoint, the server responds with a JSON object containing a simple message. This illustrates how our Express server communicates data back to the client, embodying RESTful principles for data exchange. Finally, we start the server and log a message to the console, confirming where the server is running. This fundamental application illustrates how the backend processes requests and serves data, laying the groundwork for our full-stack setup. Now that we have our server up and running, let's shift our focus to the client side. First, we will create an index.html file inside the client directory. This file establishes the structure of our HTML document, setting the character encoding and the title for the page. Importantly, it includes a script tag that references app.js, which will contain our client-side TypeScript code. Within the body of the HTML, we define an h1 element with the id message, initialized to display loading. This will serve as a placeholder for the message coming from the server. Next, we will write the TypeScript code in a file named app.ts. In this script, we will implement an asynchronous function named fetchData that utilizes the fetch API to make a GET request to our previously defined /API/data endpoint. This request allows us to retrieve data from the server. Once the data is received, it is processed as JSON and the text content of the h1 element with id message is updated with the server's response message. By fetching data in this way, we connect the client-side script to the server, demonstrating a basic dynamic interaction within our full-stack application. Now let's compile our TypeScript files to ensure that the server and client code is ready to run. We will navigate to both the server and client directories and utilize the TypeScript compiler to transpile our TypeScript code into JavaScript. This step is crucial as it converts our TypeScript code, which may contain type annotations and other features not understood by standard JavaScript engines, into pure JavaScript that can be executed in Node.js or in the browser. Next, we will start the server using Node.js to run the compiled server code. This will initialize our Express application, allowing it to listen for incoming requests on the specified port. Following this, we can serve the client files by simply opening the index.html file in a browser. This file acts as the entry point for the front-end application, allowing us to see the HTML and interact with the JavaScript code that fetches data from our backend server. Alternatively, for a more streamlined experience, we can integrate tools like Webpack or an equivalent bundler, which helps automate the build and serving processes for a smoother development workflow. Next, we will create a shared type that can be utilized by both the server and client. To do this, we will define an interface named message in a new file called types.ts. This interface simply specifies that a message will always be a string, ensuring consistency in our data structures across different parts of the application. By using this shared type, we can enforce that any data sent between the server and client conforms to this structure, reducing errors and improving clarity. Now let's take a look at how we can incorporate this shared interface into our Express server. In the index.ts file of the server, we will import the message interface from the shared types file. This allows us to specify the response type for our API endpoint. By doing so, we clearly indicate that the response object from the server will match the message interface structure, which enhances the reliability of the data being sent to the client. This small yet significant addition improves code readability and ensures that the response adheres to the defined contract. With these shared types in place, we can maintain a clean and organized code base, fostering better collaboration and reducing the potential for bugs as our application scales. Now let's implement the shared type in the client code. We begin by importing the message type from the shared directory into our app.ts file. This ensures that the data structure we expect to receive from the server remains consistent across both the front-end and back-end. Next, we create an asynchronous function called fetchData that handles retrieving data from the server. Inside this function, we make a fetch request to the /API/data endpoint, awaiting the response. Once we receive the response, we pause it as JSON and type the resulting data as message. This type assertion guarantees that the data will adhere to the defined structure, which enhances type safety and aids in reducing potential runtime errors. Finally, we target the HTML element with the ID message and update its inner text to display the message received from the server. This integration of shared types not only streamlines our code, but also reinforces the importance of maintaining a consistent data contract throughout our application. By doing so, we can ensure that our application functions correctly and efficiently as it scales, while making future refactoring easier. Now let's set up Jest, a popular testing framework, to ensure our application remains robust as we make changes. We'll begin by installing Jest along with TypeScript support, which allows us to write our tests in TypeScript. This setup is beneficial as it enables type checking during test execution, catching potential errors early on. Next, we need to create a configuration file for Jest named jest.config.js in our server directory. This file specifies that we're using tsjest for TypeScript support and establishes the environment for our tests. Additionally, it includes a setting to ignore certain directories, namely dist and node modules, ensuring that our tests only run against the relevant files. Now let's implement a test for our Express server. We will create a tests folder and an app test ts file within it. Writing this test will help us verify that the /API/data endpoint returns the expected JSON response. In our test, we utilize superdist to simulate a GET request to the endpoint and check if the server responds with a status code of 200, along with the correct message. This form of testing is crucial, as it ensures our core functionality works as intended and provides us with confidence when making further changes or enhancements. Wrap-up time. You have now successfully built a full-stack application using TypeScript that communicates between a Node.js server and a front-end client. You learn not just how to build the functional aspects, but also how to structure your project for maintainability with shared types and proper testing. As you grow more comfortable with these concepts, you can start incorporating more advanced features like authentication, database integration, and complex state management. The world of full-stack development is vast, and with TypeScript, you're better equipped to handle it all with confidence. Let's keep the momentum going. There's so much more to explore, so keep coding and remember, every great software journey begins with a single line of. Now let's take a look at how we can define a user structure in TypeScript using interfaces and mapped types. First, we create a user interface that includes 3 properties: ID, name, and email, each representing fundamental attributes of a user. This organization enables us to create a clear blueprint for our user data, ensuring consistency throughout the application. Next, we implement a map type called read-only user that utilizes the read-only modifier. This modifier is applied to all properties of the user interface by iterating through its keys with the keyoff operator. As a result, the properties in read-only user are immutable, meaning any attempts to change these values will lead to compile time errors. This approach emphasizes the importance of data integrity and immutability, effectively reducing errors in our code and enhancing our ability to manage changes safely. Thus, employing map types not only boosts our type-checking capabilities, but also promotes better practices in structuring our TypeScript applications. Now let's explore the concept of conditional types in TypeScript with a practical example. The code defines a generic type called isArrayT, which uses a conditional type syntax to check whether the type T extends an array type denoted by any. If T is indeed an array, the type resolves to the string array, whereas if it's not an array, it resolves to the string not an array. Next, we evaluate 2 scenarios using this type. In the first instance, we apply isArray to number, which results in the type being inferred as array, indicating that number is in fact an array. In contrast, when we use isArrayString, the outcome is not an array, confirming that a string does not meet the criteria of an array type. This functionality enhances our ability to write flexible and type-safe code, allowing functions and data structures to adapt automatically to varying input types based on this type-checking mechanism. Now let's see how we can implement the updateProfile function, which utilizes the partial T utility type from TypeScript. This function accepts 2 parameters, a user profile object representing the user's current profile and an updates object, which is a partial representation of user profile. By defining updates as partial user profile, we enable the function to accept an object that may contain any combination of the properties defined in the user profile interface, allowing for flexible updates. Within the function, we merge the original profile with the updates using the spread operator. This means that any properties included in the updates object will overwrite those in the original profile, while any properties not included will remain unchanged. This implementation is particularly beneficial in scenarios like RESTful APIs, where often only a subset of data needs to be modified. By using partial T, we achieve concise and efficient updates, ensuring that our code remains clean and easy to maintain. Ultimately, this method demonstrates how TypeScript's utility types facilitate more dynamic and adaptable function signatures. Now let's see how we can implement the pick utility type to create a simplified view of an existing type. In our example, we start by defining a new type called user preview that extracts only the name and email properties from the broader user profile type. This approach is particularly useful when you need to represent a limited user profile that conveys essential information without exposing all the sensitive data stored in the full profile. Next, we create a constant called user preview that adheres to the user preview type. This object contains only the name and email fields, which are critical for many scenarios, such as showing user information in a public-facing interface or API response. By utilizing the pick utility type, we enhance our code's clarity and maintainability, ensuring that only relevant details are shared, thus providing better security and reducing potential bugs that could arise from handling unnecessary data. This utility is a powerful tool in TypeScript's arsenal, allowing for greater flexibility when dealing with data types in a type-safe manner. Now let's see how we can implement type guards using the typeof operator. In this example, we define a function called example that accepts a parameter named value, which can be either a number or a string. The function includes a conditional statement that checks the type of value. If the type is determined to be a string, it logs the length of the string to the console, demonstrating how we can safely access string-specific properties. On the other hand, if value is not a string, we treat it as a number and log the square of that number. This mechanism showcases how type guards refine the possible types of a variable within conditional blocks. By employing type guards, we're able to enhance the safety and clarity of our code, effectively preventing runtime errors related to type mismatches. Through this structured approach, developers can feel more confident when dealing with variables that may hold different types, ensuring that operations performed on these variables are valid based on their actual types. Overall, this technique significantly contributes to writing robust and maintainable TypeScript code. Now let's implement the following user-defined type guard, which allows us to establish more precise type checks in our applications. In this example, we define two interfaces, dog and cat, each with distinct methods that represent their behaviors. This dog function serves as a type guard that checks whether the provided animal has a bark method, and it utilizes the animal is dog return type. This tells TypeScript that within the interact function, we can treat animal as a dog when the function returns true. Next, we use this isDog type guard within the interact function to differentiate behaviors based on the actual type of animal. By utilizing this guard, we can confidently call animal bark if the animal is a dog or animal meow if it is a cat. This design promotes type safety and decreases the likelihood of encountering runtime errors associated with incorrect type assumptions, making your code base more robust and maintainable. Now let's take a look at how we can utilize enums in TypeScript to define a set of related constants, enhancing both code clarity and type safety. In this example, we define an enum called userRole to categorize different user roles such as admin, user, and guest, each linked to a specific string value. This structured approach allows us to use these roles throughout our application without the risk of introducing arbitrary string values, which could lead to errors. Next, we implement the getUserPermissions function, which accepts a user role as its parameter. Inside the function, a switch statement determines the permissions granted based on the role passed. For example, if the role is admin, it returns a message indicating that all permissions are granted, whereas a user receives limited permissions, and a guest is given read-only access. This logical flow ensures that only valid roles are processed, reinforcing type safety and minimizing potential bugs in our application by utilizing a defined set of constants. Enums, therefore, not only improve code readability, but also promote best practices in type checking within TypeScript. Now let's take a look at how we can utilize intersection types in TypeScript to combine multiple interfaces into one cohesive structure. In our example, we define two distinct interfaces, authUser, which encapsulates authentication-related properties such as an ID and a username, and profile, which includes user-specific information like email and avatar URL. By employing the intersection operator, we can merge these two interfaces into a single type known as userProfile This new type inherits all the properties from both authUser and profile, thus enabling the creation of a userProfile object that contains complete user details. The power of intersection types lies in their ability to allow an object to be treated as belonging to multiple types simultaneously. Consequently, this opens the door for more complex structures that can represent diverse functionalities or roles within our application, leading to a more versatile and organized code base. By leveraging intersection types, you can streamline your data handling and achieve more sophisticated type safety in your TypeScript applications. Now let's implement a function that demonstrates the concept of union types in TypeScript. In the printed function, we define the parameter id to accept either a number or a string. This flexibility is beneficial because it allows the function to handle multiple types of input seamlessly without the need for complicated type checks or conversions that could clutter the code. When invoking the function, we can pass in different kinds of values, like a numeric ID such as 10 or a string ID like ABC, and the function will correctly display the ID type provided. This showcases the power of union types, which enable our functions to maintain type safety while also providing the versatility to work with various data types. In real-world applications, this approach makes our code more adaptable, ensuring that we can accommodate different types of identifiers without sacrificing clarity or maintainability. Remember, leveraging union types effectively can lead to more robust and concise code in your applications. As we wrap up this lesson, remember that mastering advanced type-checking methods in TypeScript empowers you to write more maintainable and robust applications. From map types to utility types, user-defined type guards to enums and intersection to union types, each feature amplifies your ability to control and define data structures efficiently. So dive into these concepts and incorporate them into your projects for improved clarity and type safety. Now let's implement the command to install TypeScript globally on your machine. By running npm install g-TypeScript, you are using npm Node.js's package manager to install TypeScript so that it is available in any of your projects. This global installation allows you to access TypeScript and its tools from anywhere in your command line interface, ensuring that you can start developing TypeScript applications with ease. After you've installed TypeScript, the next step is to verify that the installation was successful. You can do this by running tscv, which will display the version number of TypeScript you have installed. This confirms that TypeScript is correctly set up on your system. If you see the version number, congratulations, you are now ready to embark on your journey of building TypeScript projects. This foundation will allow you to leverage the powerful features of TypeScript that enhance your code's clarity and safety as you proceed with your development. Now that you are inside your project folder, it's a good practice to initialize your project with npm. This will create a package, JSON file that will serve as the foundation for managing your project's dependencies and scripts. By running the command to initialize npm with the Y flag, you automatically generate a default package, JSON file without needing to answer any prompts. This file includes essential metadata about your project, such as the project name, version, and description, which can be crucial for both development and collaboration. Next, we will add TypeScript as a development dependency in your project. By using the command to install TypeScript with the savedev flag, we inform npm that TypeScript is needed only during the development phase. This distinction is important because dependencies marked as dev dependencies won't be installed in production environments, ensuring that your production build remains lean and efficient. With TypeScript added, you'll be equipped to leverage its powerful features in your development workflow. This setup is vital for enhancing the coding experience and ensuring better project maintainability as you begin your TypeScript journey. Next, we will create our TypeScript configuration file, which guides TypeScript on how to compile our project. To do this, we can initiate the generation of a tsconfig JSON file by running a simple command. This default configuration file contains several key options to customize the TypeScript environment for our project. Now let's take a closer look at the essential settings within this configuration. The Compile Options section defines how TypeScript behaves during compilation. For instance, setting the target to E6 ensures that our compiled JavaScript code follows the ECMAScript 2015 standard while specifying module. Common indicates that the module system being used is CommonJS, which is prevalent in Node.js applications. Additionally, we configure the out dia to direct the compiled JavaScript files to the dist directory, whereas the root dia points to our src directory where our TypeScript files reside. The strict option is especially important as it enables strict type checking, helping to catch potential errors during development. Lastly, the include and exclude arrays specify which files to include and which to ignore during the compilation process. This structured approach helps maintain an organized and efficient development environment. Now let's see how we can implement a simple TypeScript function along with a variable declaration. In this example, we define a function called greet that takes a single parameter, name, with the type annotation string, indicating that it must be a string. The function returns a string that includes a greeting message, using template literals to incorporate the name parameter into the return string. This demonstrates the benefit of TypeScript's strong typing, as it helps ensure that only valid string values are passed to the function. Next, we declare a constant variable named username and explicitly specify its type as string, assigning it the value Alice. This serves not only as an example of variable declaration in TypeScript, but also highlights how you can define data types to improve code clarity and reduce errors. Finally, we log the result of the greet function to the console, passing in username as an argument. When executed, this will output a personalized greeting message to the console, illustrating how TypeScript enhances functionality while maintaining strong type safety. Next, we will compile our TypeScript code into JavaScript. To do this, we will run a command in the terminal that invokes the TypeScript compiler, tsc. This command tells TypeScript to read our tsconfig JSON file and compile the TypeScript files located in the specified directories. If everything is set up correctly, this process will generate JavaScript files in the dist directory, where the compiled code will reside, ready for execution. Once we have successfully compiled the code, we will execute it using Node.js by running the command node dist/app.js. This will execute the compiled JavaScript file, and as a result, we should see output in our terminal. This output will be a greeting message. Hello, Alice. Welcome to TypeScript. This demonstration not only illustrates how TypeScript enhances JavaScript with type safety during development, but also shows the seamless transformation into executable JavaScript code, highlighting the effective workflows in TypeScript development. Now let's implement a build script in our package JSON file to automate the compilation of our TypeScript code. To do this, we'll add a scripts section where we define our build command. In this case, we'll set the build script to execute the TypeScript compiler, tsc. This means that whenever we want to compile our TypeScript files into JavaScript, we simply run npm run build from the terminal. Automating the compilation process streamlines our workflow, saving us time and reducing manual steps. By encapsulating the build command in a script, we can easily execute the task without remembering the exact command or its parameters. This practice not only makes it easier for anyone working with your project to build the code, but also enables you to quickly adapt the build process if necessary. As your project grows and potentially incorporates additional TypeScript files, having this build command simplifies the maintenance of your development environment, making it more efficient and organized. Now let's explore how to enhance our TypeScript development workflow with tsnode, enabling us to run TypeScript files without needing a separate compilation step. To add this functionality to our project, we will first install the tsnode package as a development dependency. This package allows us to execute TypeScript scripts directly, making it particularly useful during the development phase when we want to quickly test our code without the overhead of compiling it into JavaScript each time. Now let's move on to the command we will use to run our TypeScript files effortlessly. By utilizing npx combined with tsnode, we can execute our app.ts file from the terminal with a simple command. This command will read our TypeScript code and run it in one go. This integrated experience streamlines our workflow and helps focus on coding rather than managing the build process, allowing for more efficient testing and debugging of our code in real time during development. In summary, we've gone over the essentials of setting up a TypeScript project from scratch. We installed TypeScript, initialized a project with npm, created a configuration file, structured our source folder, and compiled our TypeScript code into JavaScript. All these steps build a solid foundation for developing scalable and maintainable TypeScript applications. TypeScript indeed offers a robust way to manage your JavaScript development, helping you catch errors early and enhancing your project's structure. As you continue learning, remember to explore more about TypeScript's advanced features and tools to enrich your coding experience. So get out there, create your TypeScript applications, and see how much easier and more efficient your development projects can become. Happy. Now let's take a look at how TypeScript handles type inference with a practical example. In the first piece of code, we declare a variable named message and assign it a string value, hello TypeScript. Here, TypeScript automatically infers the type of message as a string, which eliminates the need for explicit type annotations. This feature simplifies our code and helps catch potential errors when using this variable without additional overhead. Next, we will implement a function called add, which takes two parameters, a and b, both explicitly typed as numbers. The function returns the sum of these two parameters. Thanks to TypeScript's type inference, it automatically recognizes that the return type of this function is also a number. This means that any time we utilize add, TypeScript will ensure that both arguments conform to the expected number type, enhancing type safety and making our code more robust against type-related bugs. This streamlined approach to type checking empowers developers to write cleaner and more maintainable code while leveraging TypeScript's capabilities effectively. Now let's examine how we can define a flexible function using union types in TypeScript. The function formatInput is designed to accept either a string or a number as its input. This flexibility is beneficial as it allows the function to handle multiple types of data while maintaining type safety. By expressing this in the function signature with string number, TypeScript ensures that any value passed to formatInput must be one of these two types. If you attempt to pass a value of a different type, such as a Boolean, TypeScript will raise a type error, helping to prevent potential runtime issues. Next, we will implement a mixed array that can store both strings and numbers. By defining mixed array with the type annotation, string number, we create an array that can contain multiple types of elements. This is particularly useful for applications that require storing diverse data types while still leveraging TypeScript's type-checking capabilities. The TypeScript compiler will enforce these rules, ensuring that all elements within mixed array are either strings or numbers, thus providing robust type safety throughout your code. Next, we will examine how to create intersection types in TypeScript. In our example, we define two interfaces, person and employee. The person interface specifies two properties, a name of type string and an age of type number. Similarly, the employee interface includes an employeeid of type number and a department of type string. Now let's implement an intersection type called employeeDetails, which combines both interfaces using the AND operator. This means that any object of type employeeDetails must include properties from both person and employee. Next, we create an employee object that adheres to the employeeDetails type, providing values for all required properties. In this case, we define the name as Alice, set the age to 30, and include the employeeid and department information. This approach demonstrates how intersection types allow us to build rich, composite types that enhance code reusability and structure. By using intersection types, we can model real-world entities more accurately, ensuring that objects have the appropriate attributes from multiple sources. Now let's explore how TypeScript enhances type safety through type guards with a practical example. In the first code snippet, we define a function called logValue, which accepts a parameter that can be either a string or a number. Utilizing the typeof operator within an if statement, we can refine the type of the variable. When value is identified as a string, the code logs it as such. Conversely, if the type is anything else, the code assumes it must be a number, leading to a different logging message. This functionality illustrates TypeScript's strength in providing localized type analysis, which ensures clarity in our code and robust handling of diverse types. Next, let's examine the concept of custom type guards. We create an interface named cat to represent an object with specific properties and methods. Then we implement the isCat function, designed to check whether a given animal object conforms to the cat interface by verifying the presence of a meow method. When we use this type guard to check an object called pet, TypeScript narrows down the type of pet within the conditional block. This allows us to safely call the meow method, illustrating how custom type guards facilitate type safety in a more nuanced manner. Now let's take a look at how we can create flexible types using map types in TypeScript. The code defines an interface named user, which has two properties, id and name. We then create a map type called partialUser utilizing TypeScript's powerful mapping capabilities. This map type iterates over each key k in the user interface and makes every property optional by appending a question mark. This transformation allows us to create an object that only requires some of the properties defined in user, enhancing flexibility in our code. For instance, we can construct a partialUser object with just the name property set to Alice without having to define an id. This feature is particularly beneficial when dealing with scenarios such as form submissions, where not all data points are mandatory. Next, we will implement another map type named readOnlyUser, which ensures that all properties of the user interface are read-only. By applying the read-only modifier to each property, we create a new type that prevents any modifications after the object is created. For example, once we instantiate read-only user with certain values, attempting to change the name property will trigger a compile time error, thereby providing a safeguard against unintended changes. Now let's explore how conditional types operate in TypeScript by implementing our own type is string. This type serves to determine whether a given type denoted as t is a string. By using the extends keyword, we can express a condition. If t indeed extends the string type, it will yield the message, yes, it's a string. Conversely, if t does not adhere to this condition, it will return no, it's not a string. Next, we will write the following types, test1 and test, to demonstrate how isString functions in practice. If we pass a string to test1, the type outputs yes, it's a string, validating our condition. On the other hand, test2, which receives a number, results in no, it's not a string. This exemplifies the dynamic nature of conditional types, allowing developers to create highly flexible and responsive type definitions that adapt based on the context of their inputs. This feature enhances TypeScript's ability to enforce type safety while promoting maintainability and clarity in your code. Now let's explore how the required utility type can enhance our type definitions in TypeScript. In our example, we define an interface called settings with two optional properties, volume and brightness. This structure allows for flexibility, but suppose we need to ensure that both properties are set whenever we create an instance of settings. Here, the required utility type comes into play. By using required settings, we transform the optional properties in our settings interface into required ones. Consequently, when we create the default settings object, TypeScript enforces that both volume and brightness must have values. In our implementation, we set volume to 50 and brightness to 70, thus conforming to the new structure dictated by the required utility. This approach not only eliminates redundant type definitions when variations of existing types are needed, but also enhances code reliability and clarity. Utility types like required are invaluable for streamlining type definitions in TypeScript, ensuring that our objects meet specific criteria without unnecessary repetition. So in this lesson, we explored several advanced type-checking techniques using TypeScript. From type inference and union types to intersection types, type guards, map types, and utility types, these features enhance your ability to write safe and descriptive code. By implementing these techniques, you can minimize runtime errors and foster a more maintainable code base. As you progress in your TypeScript journey, practicing these advanced methods will significantly aid in your development process. The beauty of TypeScript is its capability to increase clarity in your code while safeguarding against potential pitfalls. Keep experimenting, keep coding, and enjoy the incredible journey of mastering TypeScript. Happy. You want to kickstart your journey into the world of TypeScript? Fantastic. One of the first steps in your TypeScript adventure is setting up a project that suits your needs. In this session, we'll explore how to create a TypeScript project from scratch, discuss the options available to you when integrating TypeScript, and walk through some hands-on examples to make everything clear. Now let's see how we can set up our TypeScript project directory. First, we create a new folder using the command mkdir my TypeScript project, which acts as the workspace for our project. This is a foundational step in organizing our files and keeping them manageable. After that, we navigate into this newly created directory with the command cd my TypeScript project, placing us inside the project folder so we can start adding files and configuring our project. Next, it's essential to initialize our package manager, and we do this with npm initY. This command generates a default package JSON file, which is crucial for managing our project's dependencies. The package JSON serves as a metadata file, keeping track of the libraries and tools we will use throughout the development process. Setting up these basic structures allows us to efficiently build upon our project as we dive deeper into TypeScript, ensuring everything is organized from the get-go. Now let's take a look at how to install TypeScript as a development dependency in your project. By running the command to install TypeScript with the savedev flag, you're ensuring that TypeScript is included in your project without affecting your global environment. This practice promotes better project encapsulation and helps manage your dependencies more effectively. Next, we will initialize a TypeScript configuration file by using the command npx tscinit. This action creates a tsconfig JSON file in your project's root directory, which is essential for configuring how TypeScript behaves. The generated file is fully comment-enabled, meaning you can easily customize it to fit the specific needs of your project. Now let's implement how we can structure this configuration file. In tsconfig JSON, you will find a compiler options object where you can define various settings. For instance, setting target ES6 instructs TypeScript to compile your code into ES6 JavaScript. The strict true option ensures that all strict type checking is enforced, helping you catch potential errors during development. The inclusion of ease module interop and skiplib check enhances compatibility and performance, respectively, allowing for a smooth development experience. Now let's implement the following code to create a basic TypeScript file. First, we'll declare a variable named greeting, specifying its type as string. This practice not only helps clarify the purpose of the variable, but also enforces type safety, which is a core benefit of using TypeScript. By explicitly stating that greeting is a string, TypeScript will alert us if we ever try to assign a value of a different type, avoiding potential runtime errors. Next, we assign the string hello TypeScript to the greeting variable and use console.log to display it in the terminal. This simple operation showcases how TypeScript can be used to build up from basic syntax while integrating strong typing. After writing this code, it's essential to compile it into JavaScript so that the code can run in a JavaScript environment. To do this, we can execute the TypeScript compiler from the terminal. Once compiled, a new JavaScript file named app.js will be created, which is the equivalent of our TypeScript code, ready for execution and further expansion in our project. This process lays the groundwork for more complex TypeScript modules that we will explore shortly. Now let's see how to execute our TypeScript code using Node.js. The command node src/app.js is used to run the compiled JavaScript file that we generated from our TypeScript code. By executing this command in the terminal, we can see the output hello TypeScript, confirming that our setup is working correctly. Next, we will implement a module that handles user data. In our user.ts file, we define a user class with a constructor that takes two parameters, name and age. The public keyword in the constructor allows us to automatically create properties with the same names, making our class concise. This class also includes a method, getInfo, which returns a string that succinctly describes the user by combining the name and age. By using the export keyword, we make this class available for other files to import and use. Now let's take a look at how to utilize this user class in another file, main.ts. Here we import the user class and create an instance named user1 with the name Alice and age 30. Finally, we invoke the getInfo method and log the output to the console, demonstrating the modularity of our TypeScript implementation. This structure not only enhances the organization of our code, but also makes it scalable and maintainable. Next, we will compile all our TypeScript files into JavaScript, ensuring our tsconfig JSON includes all TS files in the src folder. To initiate this process, run the tsc command, which triggers the TypeScript compiler based on the configurations specified in your tsconfig JSON. This command scans your TypeScript files, checking for syntax errors, type mismatches, and other issues, while also generating the corresponding JavaScript files in the same directory structure. You should expect to see both user.js and main.js files created in your src folder. Each JavaScript file is an output of the TypeScript files you wrote earlier, which includes your user class and the main application logic. This modular approach to coding allows your applications to be structured better, where functionality is broken down into manageable sections. Now that we have our JavaScript files ready, we can run the main application using Node.js with the command to execute main.js. When you run this command, you should see the output confirming that Alice is 30 years old, demonstrating that your code works as intended and that TypeScript's strict typing has helped catch potential errors early in the development process. Now let's explore how to use the TypeScript compiler in watch mode. By executing the command npx_tscwatch, you enable the TypeScript compiler to monitor your project files for any changes. This feature is incredibly beneficial during development because it eliminates the need to manually rerun the compile command every time you make an edit. Instead, the compiler automatically recompiles your TypeScript files whenever it detects modifications, allowing you to focus more on coding rather than constant setups. This functionality enhances productivity, especially when working on larger projects where frequent edits are common. You will find that it streamlines your workflow, giving you instant feedback on your code changes. As you work, you'll appreciate how the moment you save any updates, the changes are reflected in the compiled JavaScript files without any extra steps required on your part. With this, you can maintain your coding momentum and ensure that you're always testing the most up-to-date version of your application. Now that you've got basic project setup and some advanced features under your belt, you're on your way to becoming proficient with TypeScript. Remember, whether you're building frameworks, applications, or libraries, the foundational skills you're learning now will empower you to maintain and extend your projects effectively. As you continue your TypeScript journey, explore additional features like interfaces, generics, and even brands. TypeScript is a vast language, and there's always something new under the hood. More importantly, don't forget to keep practicing, experimenting, and having fun with your code. Wrapping it all up, so far we covered a robust, foundational approach to set up a TypeScript project, including compiling and modular programming practices. Now armed with this knowledge, go ahead and explore further into advanced TypeScript features in your future projects. Remember, every line of code you write is a step closer to mastering TypeScript. Let's dive into advanced type management in TypeScript. This topic is essential for any developer working with the language, as it allows you to write more robust, maintainable code while handling complex data structures. Now let's implement a declaration file for the Lodash library to define our custom types. In this file, we begin by declaring a module named Lodash, which allows us to extend its functionality while maintaining type safety. Within this module, we define a function named concat_arrays, which is designed to take multiple arrays of the same type and concatenate them into a single array. By using generics represented by T, we make the function flexible, allowing it to handle various types of arrays, not just strings. The spread operator, arrays T, indicates that the function can accept any number of array arguments, each of which can be of any type defined by T. The return type T ensures that the output is an array of the same type as the input arrays. This setup essentially bridges the gap between untyped libraries and TypeScript's type system, enabling developers to use utilities like concat_arrays confidently. By creating such a declaration file, we enhance our project's type safety while still utilizing the powerful features of third-party libraries like Lodash. Now let's see how we can implement the concat_arrays function from our previous declaration to handle multiple string arrays seamlessly. In this code, we begin by importing the concat_arrays function from the Lodash library, which we previously defined in our declaration file. This allows us to leverage the function's type-safe capabilities within our TypeScript project. Next, we define two string arrays named string array1 and string array2. Each array holds a set of strings that we want to concatenate. We then call the concat_arrays function, passing in both arrays as arguments. The beauty of this implementation lies in the type safety that TypeScript enforces. Even though we are working with an external library, we can confidently concatenate strings without worrying about type errors. Finally, we log the result to the console. The output is a single array that combines both input arrays into one cohesive list, clearly demonstrating the function's utility. This approach effectively illustrates how to bridge the gap between untyped libraries and TypeScript's strict type system while maintaining robust, maintainable code. Next, we will write the following code that defines two interfaces, user and admin. The user interface outlines the common properties, such as name and email, that represent a basic user of the application. On the other hand, the admin interface adds an additional layer by specifying an array of permissions, which are vital for users with elevated roles in the system. To create a combination of both user types, we implement an intersection type called adminUser. This type merges the properties from both the user and admin interfaces, effectively allowing us to define an entity that embodies attributes from both definitions. Now let's create an instance of the adminUser type. This object must include all properties defined in the user and admin interfaces, ensuring that it has a name, email, and permissions. In this instance, we define an admin user named John Doe with specific permissions like read, write, and delete. This approach showcases TypeScript's ability to handle complex data structures while maintaining clear and manageable code organization, ensuring that every admin user conforms to the expected structure. Next, we will write a utility type that demonstrates how to create a more manageable representation of an existing interface using the pick utility. Here, we've defined an interface called product, which encapsulates essential properties like ID, name, price, and stock. However, in scenarios where we only need a small subset of these properties, specifically the id and name, we can streamline our code by employing pick. Now let's see how we can implement this with the product overview type. By invoking pick, we derive a new type that maintains only the specified properties from the product interface. This is particularly useful when dealing with large data structures, as it focuses on the necessary information while avoiding clutter. In our example, we create a constant called product of type product overview, initializing it with values for id and name. This enables us to work with a leaner object representing products in situations that don't require full detail, promoting cleaner and more efficient code management while still adhering to TypeScript's strong typing principles. Next, we will write code that utilizes the omit utility type to create a refined type based on the existing product interface. In this example, we define a new type called product without price, which removes the price property from the product interface. By using omit product price, we effortlessly create a type that includes all properties of the product except for the specified one. Now let's implement this by creating a constant named product without price of type product without price. Here, we provide only the remaining properties, ID, name, and stock. This showcases how we can manage data integrity by excluding unnecessary properties while still retaining useful information about the product. Using omit not only simplifies our type definitions but also helps maintain cleaner code, ensuring that objects conform to the desired structure without the overhead of unnecessary fields. This approach promotes better data management, enhancing our application's robustness as we move to more complex TypeScript scenarios. Now let's take a look at how we can utilize conditional types in TypeScript. The isString type is an excellent example of this feature as it allows us to determine whether a given type T is a string. The syntax leverages the extends keyword, which checks if T satisfies the condition of being a string. If this condition holds true, isString will return the string literal yes, it is a string. However, if T is not a string, it yields the response no, it is not a string. This dynamic evaluation is incredibly powerful. For instance, when we define test1 and assign it the type isString, the evaluation outputs yes, it is a string, indicating that string meets the conditional requirement. Conversely, test2 evaluates isString number, which returns no, it is not a string. This illustrates the reactivity of conditional types, allowing us to construct versatile APIs that can adaptively respond to different data input types, enhancing the type safety and flexibility of our TypeScript applications. Now let's take a look at how we can define a simple interface and utilize map types for flexibility in our code. We start by creating an interface called person, which has two properties, name of type string and age of type number. This interface serves as a template to define the structure of our data. Next, we will implement a map type called partial person. Here, we leverage TypeScript's powerful capability to transform properties. By using the syntax k and key of person k, we make every property of person optional in partial person. This means that when we create an object of type partial person, we can freely choose which fields to include, or we can even omit all. Now let's see how we can use this in practice by creating instances. For example, we can create an object named person1 with just the name property and another object person2 with only the age property. This demonstrates how map types enhance flexibility, allowing for the construction of more adaptable data models that suit varying needs without rigid constraints. So as we've explored advanced type management in TypeScript, we uncovered methods for bridging the gap between typed and untyped libraries, effectively using intersection types, utility types, conditional types, and map types. As you grow as a developer, mastering these concepts will greatly enhance your ability to manage complex coding scenarios, making your applications robust and easier to maintain. Always remember, TypeScript is a powerful tool, enabling you to write expressive, safe, and manageable code, transforming even the most complex structures into comprehensible parts. With these advanced techniques, you're well on your way to becoming a TypeScript expert. Happy. You want to get started with TypeScript? Fantastic. The big question is, how do you start? You can integrate TypeScript into your projects in many ways, and all are slightly different depending on your project's needs. Today, we'll delve into project setup techniques that cater to varied requirements, particularly if you're working on Node.js applications or front-end development. So far, we learned about basic TypeScript project setup, including initializing a Node.js project, managing dependencies, and creating configuration files. We have delved into modular programming with classes and explored strategies for incorporating external libraries lacking type definitions through declaration files. Additionally, we discussed advanced concepts like intersection types, utility types such as pick and omit, conditional types, and map types, allowing for more flexible and manageable type definitions. These advanced techniques enhance your TypeScript skills, aiding in the development of robust applications. Now, we will cover project setup techniques that cater to differently structured projects. Next, we'll initialize a TypeScript project that uses Node.js, starting with a simple yet essential step, setting up the project directory and initializing it with npm. We begin by executing the command that creates a package, JSON file, which acts as the backbone of our project, holding important information about dependencies and project settings. Now let's install TypeScript as a development dependency. This ensures that TypeScript is available during the development and compilation of our files, but won't be included in any production environment. This setup allows us to maintain a clean and efficient production build while leveraging TypeScript's powerful typing system in our development workflow. With TypeScript installed, we can move forward confidently, knowing that we can compile our TypeScript code into JavaScript. This process switches us from writing plain JavaScript to leveraging TypeScript's features, enhancing our overall development experience with type safety and improved code quality. Next, we will initialize a TypeScript configuration file, which is essential for defining how TypeScript compiles your code. By executing the command to initialize TypeScript, a file named tsconfig.json is created in your project's root directory. This file contains various compiler options that direct TypeScript on how to process your source files. For instance, the target option specifies that the compiled output should be compatible with ECMAScript 2016, ensuring broader compatibility with JavaScript environments. The module option is set to CommonJS, which is the module system supported by Node.js, allowing seamless integration with its architecture. Enabling ease module interop allows you to use default imports from CommonJS modules, enhancing compatibility with JavaScript libraries. The strict setting promotes stronger type checking throughout your project, encouraging you to explicitly define variable types to reduce potential errors. There's also consistent casing in file names, which prevents issues related to inconsistent character casing in file names, and skiplib_check, which optimizes the compilation process by skipping type checking of declaration files. This configuration lays a strong foundation for your TypeScript project, setting the stage for efficient and error-resistant development. Next, we'll create our initial TypeScript file. First, we need to set up a folder named src where all our TypeScript files will reside. This helps keep our project organized and separates the source files from compiled output. Inside this src folder, we will create a file called index.ts where we will write our TypeScript code. Now let's implement a simple hello world program. In index.ts, we define a constant function named greet that takes a name parameter of type string and returns a greeting message formatted as a template literal. By using TypeScript's type annotations, we ensure that the input is always a string, allowing for easier debugging and better code quality. Following this, we'll call console.log to print the greeting for the name world. This demonstrates TypeScript's ability to work with modern JavaScript features like template literals while enforcing type safety. Finally, after writing our code, we'll run the TypeScript compiler using the command npxtsc, which will transpile our TypeScript into JavaScript and generate a dist directory containing the compiled files. This step is crucial as it prepares our code for execution in a JavaScript environment. Now let's see how we can implement a basic Express server within our TypeScript project. First, we import the Express framework, which enables us to create a server that can respond to incoming requests. We instantiate an Express application by calling the Express function, which sets up the necessary infrastructure to build our web server. Next, we define a constant named port, which retrieves the port number from the environment variables or defaults to 3000 if none is specified. This ensures flexibility in deployment, allowing us to configure the port when needed. Now let's implement a simple route using the app-get method. Here we define a route for the route URL /, which takes a request and response object as parameters. When a user navigates to this URL, the server sends back a greeting message, "Hello world" from Express. Finally, we set the server to listen on the specified port using applisten. This method not only initiates the server, but also logs a message to the console to confirm that it is running successfully, making it easier to identify issues during development or deployment. Now let's see how we can configure our TypeScript project to support both TypeScript and JavaScript files. The code provided allows you to enable the coexistence of JS files while setting up TypeScript, making the migration from JavaScript to TypeScript smoother. By including allow.js true in the compiler options section, TypeScript will acknowledge and compile, JS files, allowing you to gradually transition your codebase without the immediate need to convert every file to TypeScript. Additionally, the check.js true option enables type checking on your existing JavaScript files. This means that even as you start changing your code, you can receive immediate feedback about potential type errors in your JavaScript, helping guide your refactoring efforts. This setup is particularly useful in large code bases where a full migration to TypeScript can be overwhelming. By taking this incremental approach, you can ensure that your project remains functional and maintainable throughout the transition period. Now let's take a look at how to implement a function using JS.doc to provide type information in your JavaScript code. We will write a function named addVat that calculates the total price including value-added tax, VAT. The function takes two parameters, price and VAT, the latter of which has a default value of 0.2, representing 20% VAT. To enhance type safety, the JS.doc comment above the function clearly states the expected types for each parameter and the return type. It specifies that both price and VAT should be of the type number, and that the function returns a number. This structured comment format allows developers to get immediate feedback on type matches without fully converting the file to TypeScript. When the function is called, it computes the total price by multiplying the price by 1 plus VAT, effectively adding the VAT to the original price. This approach allows you to gradually migrate to TypeScript while still benefiting from type validation through JS.doc, ensuring that your JavaScript files maintain some level of type safety during the transition. Now let's take a look at how to configure TypeScript for both server and client environments. First, we define the server's configuration with specific parameters tailored for a Node.js context. This configuration specifies that the target JavaScript version is set to ease next, allowing for the latest JavaScript features. The module system is defined as CommonJS, which is standard for server-side applications. The output directory is set to a dist-server folder, ensuring that compiled files are organized and separated from the source code. The root directory is specified as the current directory, and it includes types related to Node.js to ensure type safety when utilizing Node's built-in modules. Enforcing strict type checking encourages thorough type definitions, minimizing potential errors. Next, we will implement the client-side configuration, which also targets ease next. However, here the module system is set to ease next to support modern front-end frameworks and libraries. Similar to the server setup, the output directory is dist client, allowing for clean separation of client-side files. The root dir is kept as the current directory, while the configuration includes both DOM and easeNext libraries, enabling developers to work effectively with web APIs and utilize newer JavaScript features. This dual configuration setup aids in managing dependencies and outputs tailored to each environment, enhancing project organization and maintainability. Having understood the various techniques for setting up a TypeScript project, you have the tools to create a structured, organized, and type-safe codebase. As projects grow, maintaining clear configurations will simplify debugging and enhance overall productivity. Each environment can operate independently, yet benefit from the collective type safety TypeScript offers. This wraps up our exploration of project setup techniques. Now you are ready to dive deeper into TypeScript and use these practices to elevate your development workflow. In this lesson, we are diving into advanced type management strategies in TypeScript, particularly focusing on how to enhance your type system without completely rewriting your existing JavaScript code. We have previously covered the initial steps for setting up a TypeScript project, installing TypeScript, and creating configuration files. We also explored managing dependencies, transitioning from JavaScript to TypeScript, and creating separate configuration files for different environments. Now, we will talk about a unique approach I like to call types on the side, which allows you to write TypeScript syntax for object types and advanced features while maintaining JavaScript for your actual application. Gradual adoption has always been a primary objective of TypeScript. It's not just about jumping into the deep end, it's about wading in and getting comfortable with the water. With this technique, you can smoothly introduce TypeScript's powerful features while still leveraging the flexibility and familiarity of JavaScript syntax. This approach allows for robust type management in your projects without getting overwhelmed. Instead of clunky JS.doc comments, we can integrate TypeScript's object types, generics, and conditional types seamlessly into JavaScript. Let's see how this works in more detail. Now let's see how we can implement a user type in TypeScript to define user-related data accurately. We start by declaring a type called user, which consists of several fields including ID, name, email, and is active, each assigned a specific type. This structure not only enhances the readability of our code, but also ensures that any object adhering to this user type contains all the necessary information. By utilizing TypeScript's type system, we can create clearer contracts in our code, reducing ambiguity. Next, we will write a function named createUser that accepts an argument of type user. This function demonstrates how we can enforce type safety by ensuring that only properly structured objects can be passed in. Within the function, we simply log a message that confirms the creation of a user, incorporating the user's name into the console output. If a developer attempts to use an object that doesn't conform to the user structure, TypeScript will flag it as an error during compilation, catching potential bugs early and promoting a healthier development process. This approach illustrates the power and clarity that TypeScript can bring to object-oriented programming in JavaScript applications. Now let's implement a simple generic function that demonstrates TypeScript's capability of working with various data types while still ensuring type safety. We write a function named identity that accepts a type parameter t, serving as a placeholder for any type we want to pass. This function takes a single argument, arg, of type t and returns it. This design allows us to maintain the type received at the function call, which is inferable by the TypeScript compiler. Next, we'll see how we can utilize this identity function with specific types. By calling identity with a number, we specify that our argument is of type number, and TypeScript ensures that the type is correctly inferred with the variable num. Similarly, when we pass a string, we define its type as string with the variable str. This example showcases how generics facilitate code reusability and promote better type management, allowing us to define functions capable of handling various data types without compromising type safety. This is particularly beneficial as we dive deeper into advanced types in TypeScript, making our code both flexible and predictable. Now let's take a look at conditional types in TypeScript, which allow us to create types based on certain conditions. In the following code, we define a type called isString that evaluates whether a given type t is a string. If t extends from the string type, isString resolves to a specific string literal indicating that it is indeed a string. Otherwise, it returns a different string literal stating that it is not. This feature is powerful for creating type checks that can adapt based on the input type. Next, we will write two test cases using this conditional type. The first one, testString, applies isString to a string type and will resolve to the affirmative outcome that it is a string. In contrast, the second test case, testNumber, utilizes isString with a number type, which leads to the negative conclusion that it is not a string. This illustrates the dynamic nature of TypeScript's type system, enabling us to formulate complex type scenarios and enhancing type safety in our applications. Now let's implement a flexible structure for handling API responses using TypeScript's generics. We start by defining the API response interface, which is designed to accommodate any data type by accepting a type parameter t. This versatility allows us to create a consistent response format while still working with diverse data types, whether it's user information or product details. Next, we'll define the handle API response function. This function takes an argument of type API response t and checks for the presence of an error. If an error exists, it logs the error message to the console, ensuring that any potential issues are promptly flagged. If there is no error, the function proceeds to log the received data, showcasing the flexibility of the implementation. Now let's see how we can utilize this function by creating specific API response instances, such as user response, which conforms to API response user, representing user data. Similarly, we create product response for product data using a different structure. This approach exemplifies how we can maintain strong type safety while handling multiple data types in a streamlined manner, thus reinforcing TypeScript's strengths in managing complex data interactions effectively. Now let's see how we can use TypeScript's utility types to enhance our type management. The partial utility type allows us to create a new type based on an existing one, specifically by making all of its properties optional. For example, when we define useInput as partial user, we're essentially indicating that any object of this type can have any combination of the user properties, which is particularly useful for scenarios like form submissions, where not all fields need to be filled out. On the other hand, we have the required utility type, which ensures that all properties of a type must be defined. By declaring complete user as required user, we are enforcing that any object of this type must include every property of the user type. This is beneficial when we need to ensure that full user information is provided before proceeding with any operation that depends on that data. Moreover, the pick utility type is valuable for scenarios where we need to create a new type composed of only specific properties from an existing type. For instance, user contact info allows us to create a type that includes only the name and email from the user type, focusing on relevant information for contact situations without cluttering our logic with unnecessary fields. These utility types truly empower us to manage types effectively and adapt our structures as needed. As we wrap up, it's essential to understand that integrating these advanced type management strategies can lead to far cleaner, more maintainable code in the long run. Instead of relying on less efficient methods like JS.comments, you can harness the power of TypeScript's type system to enforce contracts, catch errors early, and provide clarity on what your functions and components expect. Remember, the goal of employing these strategies is not only to make your code safer, but also more enjoyable to work with. By organizing your types carefully and leveraging generics, conditional types, utility types, and other advanced features, you can build applications that are robust, reusable, and maintainable over time. So dive into your projects, experiment with these features, and watch how they can dramatically enhance your development workflow. Thank you for joining me in this lesson on advanced type management strategies in TypeScript. Now let's dive into the exciting world of setting up a project in TypeScript. If you're eager to get started with TypeScript, you're in the right place. The big question is, how do you start? Don't worry, by the end of this video, you'll have the clarity and confidence to begin your journey with TypeScript. So far, we covered advanced type management strategies in TypeScript, focusing on integrating TypeScript features without fully converting JavaScript code. We delved into defining object types, used generics for reusable functions, and utilized conditional types for dynamic type checks. We also discussed utility types like partial, required, and pick, all aimed at promoting cleaner, safer, and more maintainable code. Now we will focus on getting our TypeScript project set up, including environment configuration and initial code structures. Now let's explore how to initialize our TypeScript project and install the necessary dependencies. First, we will execute the command to generate a package, JSON file with default settings by using npm init. This file is crucial as it includes important metadata about our project, such as dependencies and scripts. By automating this setup with the Y flag, we skip the interactive prompts, allowing for a quicker setup process. Next, we will install TypeScript as a development dependency using npm install dTypeScript. Installing TypeScript locally is essential because it helps manage versions specific to our project and prevents conflicts with other projects we might be working on. The D flag specifies that TypeScript is a development-only dependency, meaning it won't be included in the production build of our application. With these commands now executed, we have laid the groundwork for our TypeScript project, enabling us to take full advantage of TypeScript's features as we develop our application. Now that we have our TypeScript installation squared away, it's time to initialize our TypeScript configuration. To do this, we will use the command npx tscinit, which creates a tsconfig JSON file in our project directory. This file is crucial for TypeScript's operation, as it specifies how the TypeScript compiler TSC should behave when processing the code in our project. Next, let's take a look at the contents of the tsconfig JSON file. Within the compiler options section, we define several key settings. The target option indicates the version of JavaScript we want TypeScript to compile to, with ease 2016 as a commonly used choice. The module option specifies the module system we are using, set to Commons for Node.js applications. The ease module interop option allows smooth interoperability between CommonJS and ES modules, simplifying module imports. Enabling strict ensures that TypeScript conducts robust type checking, a best practice for catching potential errors early. Lastly, the FOSS consistent casing in file names and skiplib check options help maintain consistency and optimize the compilation process. Overall, this configuration lays the groundwork for a reliable TypeScript development environment. Next, we will set up our directory structure, which is crucial for maintaining organization as your TypeScript project grows. A common practice is to create a src folder where all your TypeScript files will reside, along with a tsconfig JSON file to manage your project's configuration. The tsconfig JSON is vital as it allows TypeScript to understand how to compile your code according to specified options. Now let's write the following initial TypeScript code in our index.ts file. In this code snippet, we declare a constant named message. By adding the type annotation, string, we are explicitly declaring that this constant will hold a string value. This promotes type safety, which is one of the key benefits of using TypeScript as it helps catch errors during compilation. We then proceed to use console log message to print the value of message to the console. This basic code serves as our entry point to test if the TypeScript setup is working correctly, and it's the first step in getting comfortable with TypeScript syntax and features. Now let's explore how to compile our TypeScript project and run the generated JavaScript code. To start the compilation process, we'll use the command npx_tsc. This command invokes the TypeScript compiler, which reads our TypeScript files and generates corresponding JavaScript files based on the settings defined in our tsconfig JSON. Once the compilation is successful, you will find a new index.js file created in the specified output location, usually the same folder as our TypeScript files. Next, we will execute the generated JavaScript file using Node.js with the command node src/index.js. This command runs our JavaScript code, and if everything is set up correctly, you should see hello TypeScript displayed in your terminal. This whole process showcases the end-to-end workflow of taking TypeScript code, compiling it down to JavaScript, and executing it within a runtime environment. It's a great demonstration of how TypeScript enhances development with its type system and tooling, while still allowing for the ultimate execution in plain JavaScript. Next, we will discuss how to enable type checking in your JavaScript files using TypeScript. To activate this feature, we start by adding a special comment at the top of our JavaScript file at TSCheck. This instructs TypeScript to analyze the file for any potential type errors, allowing us to gradually adopt TypeScript without needing to convert our entire codebase immediately. Now let's take a look at an example. We first declare a variable named SumValue and initialize it with a number 42. TypeScript infers that SumValue is of type number. However, when we later attempt to assign a string value, TypeScript is cool. To SumValue, TypeScript triggers a type error. This occurs because assigning a string to SumValue contradicts the initial type inference. By using this feature, we can catch such errors early in our development process, enhancing code reliability and ensuring that our JavaScript files adhere to the types we expect. This incremental adoption is a powerful way to improve our JavaScript code quality while gradually incorporating TypeScript's robust type system. Now let's take a look at structuring our full-stack application with separate directories for both the client and server components. We'll begin by creating a client directory, where we will set up a tsconfig JSON tailored for our front-end environment. In this configuration, we specify options like the target ECMAScript version and the module system to use, selecting snext to ensure compatibility with modern JavaScript features. Importantly, we also include the DOM library, as the client-side code will interact with browser APIs. The out.dia is set to a designated folder for compiled files, helping us maintain an organized project structure. Next, we will set up a server directory that contains its own tsconfig JSON. This file will have similar options but will specify commons for the module system, which is typically used in server-side Node.js applications. Like the client configuration, it requires strict type checking to catch potential errors early in development. By utilizing separate configurations, we can effectively manage dependencies and settings for each environment, leading to a more robust and maintainable application overall. Now let's compile our TypeScript project. To do this for the client-side code, navigate to the client directory and execute the TypeScript compiler command with the specific configuration file. This command will instruct the TypeScript compiler to read the tsconfig JSON file located in the client directory and compile the TypeScript files according to the settings specified therein. Similarly, for the server side, you will need to navigate to the server directory and run the same command. This action allows the server code to be compiled in its own context, using the settings defined in the server/tsconfig JSON. By having separate configurations for the client and server, you ensure that each environment can handle its dependencies and settings efficiently. This structure not only keeps your project organized, but also enhances maintainability as your application grows. With this setup, you're effectively managing two distinct parts of your full-stack application, while leveraging TypeScript's powerful features to enforce code quality across both the client and server. Now let's see how we can incorporate the popular utility library Lodash into our TypeScript project. To do this effectively, we first need to install the type definitions for Lodash, which can be accomplished using npm By running the command to install at type/lodash, we ensure that TypeScript recognizes the types associated with this library, allowing us to leverage its full potential without encountering type errors. Next, we will import Lodash into our TypeScript file. This is done with the syntax import from Lodash, enabling us to use all of Lodash's functionalities. One of the powerful features of Lodash is its ability to manipulate arrays effortlessly. For instance, we can utilize the flatten deep method to flatten nested arrays into a single array. In our example, we pass a deeply nested array to this method, and it returns a new array with all elements at a single depth. We can then print this result to the console, which provides a clear demonstration of how Lodash simplifies array manipulations, making our code cleaner and more maintainable while enhancing overall type safety in the process. Now, as you move forward with your TypeScript project, keep in mind the importance of type safety, clear project structure, and leveraging TypeScript's powerful features to enforce code quality. As you build more complex applications, you'll appreciate the benefits that TypeScript brings to your workflow. Stay curious and keep coding. In our next session, we'll dive deeper into more advanced TypeScript features, so be sure to check it out. If you're looking for a way to enhance your JavaScript projects without diving deep into complexities, you're in the right place. Today, we'll explore how to implement basic type checking for JavaScript using TypeScript with minimal effort. So far, we learned how to set up a TypeScript project, including installing TypeScript and initializing the configuration file. We organized our project structure with proper directories for client and server applications, ensuring clear separation and tailored configurations. We also discussed checking JavaScript files for type errors and utilizing type definitions for libraries to enhance code quality. As we progress, we will cover the practical steps to get JavaScript files type-checked with TypeScript. Getting started with type checking in JavaScript can feel a bit daunting, especially if you're used to the dynamic nature of JavaScript. However, with TypeScript, you can add a layer of safety that helps catch errors early in the development process. The key to an effective transition is the simplicity of using comments in your JavaScript files. By adding a special comment directive, you can instruct TypeScript to check the types in your JavaScript code. Let's dive into that. Now let's see how we can implement basic type checking in our JavaScript code by using a simple function example. We start by introducing the addNumbers function, which takes two parameters, a and b, and returns their sum. However, to see the benefits of type checking, we call this function with a number and a string. This scenario helps illustrate how TypeScript's type-checking mechanism can prevent unforeseen errors, as it will flag the second argument, pointing out that you cannot reliably add a number to a string without coercion. When you run this code with the TypeScript compiler activated, it will alert you to this type mismatch, showcasing how type-checking can catch potential runtime errors early in the development process. This example emphasizes the need to be careful with data types in dynamic languages like JavaScript, and highlights the importance of TypeScript in providing an additional layer of safety. By observing how this function behaves, you can better understand the value of integrating type checking into your JavaScript projects with TypeScript, ultimately leading to cleaner, more maintainable code. Now let's implement the following code that adds type safety to our addNumbers function using JS-doc annotations. By defining type annotations for the parameters a and b, we specify that both must be of type number. This explicit declaration communicates to TypeScript exactly what types we expect, reducing the likelihood of errors. For example, calling addNumbers 510 will trigger a type error since the second argument is a string, which is not compatible with the expected type. Moreover, we include a return type annotation, indicating that the function will return a number, in this case, the sum of a and b. This clarity helps ensure that any future developer or yourself understands the intended use of the function at a glance, facilitating maintenance and collaboration. The type checking provided by TypeScript acts as a safety net during development, allowing us to catch potential issues before they escalate into runtime errors. Thus, implementing these type annotations enhances the robustness of our code while maintaining its simplicity. Now let's take a look at how we can define and utilize custom types in JavaScript using JS-doc in conjunction with TypeScript's type-checking capabilities. In the following code, we create a user type, which is an object that contains a name property of type string and an age property of type number. This allows us to clearly define the structure of a user object, making our code more predictable and easier to understand. Next, we implement a function called greetUser, which takes a user object as an argument and logs a greeting message that includes the user's name and age. By enforcing the user type for the parameter, we ensure that any object passed to this function must adhere to the specified structure. As we create two example user objects, user1 and user2, we see how TypeScript can catch mismatches. While user1 perfectly matches the user type, user2 contains an invalid age value, a string instead of the expected number. If we try to call greetUser with user2, TypeScript will produce an error, illustrating how type checking can help us enforce data integrity in our functions. This practice ultimately leads to cleaner and more maintainable code, enhancing our development experience. Now let's see how we can implement type checking with a popular utility library called Lodash. First, we begin by installing the type definitions for Lodash using npm, which allows TypeScript to understand the types used within this library. By adding the special comment directive at TSCheck at the top of our JavaScript file, we activate TypeScript's type checking capabilities. Next, we'll import Lodash into our file, making its utility functions accessible. In the function getUniqueNumbers, we define a parameter called numbers, which is expected to be an array of numbers. The function utilizes Lodash's unique method to filter out duplicate values from this array, returning only unique numbers. The JS doc comment above this function not only describes the expected input and output types, but also serves as documentation for anyone who might use or modify this function in the future. Finally, we'll create an array of numbers that includes duplicates and call getUniqueNumbers with this array. The function works seamlessly, returning an array of unique values, showcasing how type checking helps maintain code integrity and provides confidence in our implementation with the safeguards offered by TypeScript. Now let's implement a class that represents a bank account to manage our funds effectively. We start by defining a bank account class using JS doc annotations to specify the types of its properties and methods, enhancing type safety. The constructor takes two parameters, owner, a string representing the account holder, and initial balance, a number corresponding to the initial amount in the account. Now let's take a look at two key methods, deposit and withdraw. The deposit method accepts an amount, which must be a positive number. If an invalid amount is provided, the method throws an error, ensuring that deposits maintain their integrity. The withdraw method also takes an amount parameter, but before proceeding with the withdrawal, it checks if sufficient funds are available. If the withdrawal amount exceeds the current balance, an error is thrown to indicate insufficient funds. Finally, the getBalance method simply returns the current balance of the account. By utilizing this class structure, we can safely manage our banking operations while adhering to the principles of type safety and error handling, reinforcing good programming practices. To wrap things up, not only does type checking help you catch potential errors, but it also enhances your development workflow by guiding you with clear definitions and expectations. With TypeScript working its magic in the background, you can work on your JavaScript files with newfound confidence, knowing that you'll receive immediate feedback regarding type safety. So whether you're dealing with simple functions, complex objects, or third-party libraries, implementing type checking can ultimately lead you to a smoother coding experience. In our next lesson, we'll dive even deeper into more advanced TypeScript features that can further enhance your development process. From generics to advanced utility types, there's so much more to explore. So keep coding, keep experimenting, and don't hesitate to embrace the power of TypeScript in your projects. Happy. You want to get started with TypeScript? Fantastic. The big question is, how do we set up our project effectively? In this lesson, we'll break down the steps for setting up a TypeScript project from scratch, integrating it smoothly into your workflow, and maximizing its potential. So far, we learned how to set up a TypeScript project, enabling basic type checking in JavaScript files through the use of comments and JS doc annotations. We explored the importance of type definitions for functions and custom types, helping to catch type-related errors early. Additionally, we discussed how to seamlessly use libraries with TypeScript by installing type definitions and provided examples of integrating type safety within classes. Now we will delve into more advanced TypeScript features to enhance our coding practices further. Now let's implement a TypeScript function that will greet the user. In our index.ts file, we define a function named greetUser that takes a single parameter called name, which is of type string. This allows TypeScript to enforce type checking, ensuring that the argument passed to the function is always a string. The function constructs a personalized greeting message and returns it. After defining the function, we instantiate a variable named user and assign it the string value Alice. We then call the greetUser function with this variable and log the result to the console. This simple example not only demonstrates the process of defining a function and using a parameter in TypeScript, but also showcases the benefits of type safety by ensuring that any errors related to data types are caught early during compilation. By running this code through the TypeScript compiler, we can validate its correctness, resulting in an equivalent JavaScript file. This model forms the backbone for more complex TypeScript applications, emphasizing good coding practices from the start. Now let's write a simple TypeScript function that will greet users. In this code sample, we define a function named greetUser that accepts one parameter, name, which is of type string. This showcases TypeScript's ability to enforce types at a function level, ensuring that the correct types are utilized. The function then constructs a greeting message using a template literal, enhancing readability and maintainability. Following this, we declare a variable called user and assign it the string value Alice. Finally, we utilize console.log to output the result of invoking the greetUser function with user as the argument. This simple interaction not only demonstrates TypeScript's basic features, but also illustrates how it compiles to JavaScript seamlessly, allowing us to create dynamic and type-safe web applications. Once we have written our code, it's essential to compile it to see the JavaScript equivalent. To achieve this, we will run the TypeScript compiler command in our terminal. This will generate a corresponding index.js file in the same directory, which we can run using node.js to observe the greeting in action. Now let's expand our TypeScript code by introducing an interface, which is a critical feature of TypeScript's type system. Here, we will define an interface named user, which will establish a blueprint for what a user object should look like. The user interface specifies that any object of this type must have a name of type string and an age of type number. Next, we'll implement a function called displayUser, which will accept a user type parameter. This function formats a string that describes the user, combining their name and age for a clear output. By declaring user1 as an instance of type user, we ensure that it adheres to the structure set by the interface, thereby enforcing type safety. Now let's see how TypeScript provides immediate feedback. If we make a mistake, such as assigning a string instead of a number for the age property, TypeScript will generate an error during compilation. This feature greatly enhances our coding experience by helping to identify potential bugs early in the development process, leading to more robust and maintainable code. Now let's implement a generic function that demonstrates the power of TypeScript's type system. We create a function called getLastItem, which accepts an array of any type, illustrated by the type parameter t. By using generics, this function maintains type safety while allowing the flexibility to work with various data types. Inside the function, we simply return the last element of the array using length1. This means that whether the array consists of numbers, strings, or any other type, TypeScript will ensure the returned type is consistent with what was passed in. Next, we can evaluate the versatility of this function by passing an array of numbers and logging the last number identified. Similarly, we can create an array of strings and capture the last string, verifying that our function works correctly for different types. This highlights how generics not only foster reusability, but also maintain type safety across function calls, allowing you to develop flexible, type-safe applications. Now let's implement a function that simulates fetching user data from an API using asynchronous programming in TypeScript. The first piece of this code is an interface named userData, which defines the structure of the user data we expect to retrieve. It specifies that each user will have an id of type number and a name of type string, providing clarity on the expected shapes of the data. Next, we create the fetchUserData function, which takes an id as its parameter and returns a promise that resolves to userData. Inside this function, we use setTimeout to simulate a delay of 2 seconds, mimicking the time it might take to fetch data from an actual API. Once the delay is complete, we resolve the promise with a user object containing the passed id and a generated name. Then we define the displayFetchedUser function as an asynchronous function. Inside it, we use the await keyword to pause the execution until the fetchUserData function resolves, enabling us to handle the fetched user data seamlessly. Finally, we log the fetched user's name and ID to the console, showcasing the power of asynchronous operations to keep the application responsive while waiting for data. As we wrap up this session on project setup in TypeScript, it's vital to emphasize the importance of integrating TypeScript into your workflow effectively. By meticulously structuring your projects, leveraging TypeScript's type system, and utilizing advanced features such as generics and asynchronous programming, you can significantly enhance the quality and maintainability of your code. We've learned not just how to set up a basic TypeScript environment, but also how to employ its powerful features to create error-resistant applications. With every lesson, you're equipped to tackle more complex scenarios and produce cleaner, more robust JavaScript code. So whether you're building simple scripts or complex applications, TypeScript is designed to help you write a better experience for you and your users. Thank you for joining this lesson on TypeScript project setup. Keep coding, keep exploring, and let's make your next project a success. Now let's implement the directory structure for our full-stack application. We start by creating a main folder named My Full Stack App, which will host both our client and server directories. This organization allows for a clear separation of concerns, where the client folder can accommodate our front-end framework, while the server folder will hold our backend code. Next, we proceed to initialize the server side of our application as an npm project, which generates a package, JSON, file essential for managing dependencies. Now let's take a look at how we can install the necessary dependencies for our Node.js environment. We'll include Express, a popular web framework for Node, alongside TypeScript and the required type definitions for both Node and Express. Installing tsNode will enable us to run TypeScript files directly, simplifying our development process. Next, we need to set up TypeScript with a tsconfig JSON file where we configure important compiler options. This includes defining the output and root directories, enabling strict type checking, and allowing interoperability between module systems. Such configurations ensure that our TypeScript code remains organized and type-safe as we develop the server-side functionality. Now let's implement the configuration file for the client-side TypeScript project. We'll start by initializing a TypeScript configuration file using the command to create a tsconfig JSON. This file is crucial as it defines how TypeScript will compile our client-side code. Next, we'll define the compiler options. The target option is set to ES6, which allows us to use modern JavaScript features. We specify module to be used next, enabling the latest JavaScript module syntax. Crucially, the JSX option is set to React JSX, which is required for React applications as it allows TypeScript to compile JSX into standard JavaScript effectively. The outDia option tells TypeScript where to place the compiled files, while rootDia indicates where to find the source TypeScript files. We also enable strict type checking by setting strict to true to catch potential errors early. The ease module interop option ensures compatibility between common module types, and skiplib check speeds up the compilation process by skipping type checking of declaration files. With this configuration, your client application will be well organized and ready to handle TypeScript's robust features effectively. Now let's implement the user form component, which will serve as a form for adding users in our application. In this component, we start by importing the necessary dependencies, including React and the user interface from our shared codebase. We utilize the useState hook to manage the user input within the form. The initial state contains default values for the user's ID, name, and email. Next, we define a handleChange function that updates the user object as the input fields are modified. This function uses a React event to capture the input's name and its new value, dynamically updating the state without mutating it directly. Moving on, we create a handleSubmit function that handles the form submission. When the form is submitted, it prevents the default behavior and makes an asynchronous post request to our Node.js server. This request sends the user data in JSON format, adhering to the structure defined by the user interface, ensuring type safety. Finally, the component returns the JSX for the form, which comprises two input fields for the user's name and email, and a submit button. This structure allows users to add their information seamlessly, demonstrating the interaction between our client and server using TypeScript. Now let's implement the user submission feature in our client application. First, we set up a user form component using React, which allows us to gather user input for the name and email. We utilize React's useState hook to manage the form's state, initializing a user object with default values. This helps ensure that our form has controlled inputs, making it easier to track user input as it flows into our application. Next, we implement handleChange and handleSubmit functions. The handleChange function updates the user state whenever an input field changes, allowing us to dynamically capture user input. For form submission, the handle submit function prevents the default form behavior and instead sends a post request to our Node.js server at the specified endpoint. We use the fetch API to send the user data as JSON, ensuring our server receives the correctly structured information per the shared user interface. This integration showcases how we can leverage TypeScript's type safety while managing state in a React component, providing a seamless interaction between the client-side user interface and the server-side data handling. By doing this, we ensure that inputs are consistently validated, leading to a more robust application. You want to get started with TypeScript? Fantastic. The big question is, how do you start? Today, we're diving deep into project setup fundamentals for TypeScript, a powerful superset of JavaScript that adds static types, enhancing your code quality and readability. If you're keen on creating robust applications, learning proper setup is crucial. Let's get started. So far, we learned how to create a full-stack application using TypeScript, focusing on setting up project structures for both client and server sides. We configured NPM projects and TypeScript for a Node.js server and a React client, allowing the sharing of code through a shared directory. Additionally, we implemented a simple user interface that interacts with the server for user management, ensuring type safety with shared types. This foundational setup allows for efficient development practices and seamless integration between client and server. Now we will dive into how to set up your project effectively, ensuring every piece is in place for a smooth development experience. Now that we've created our project directory, the next step is to initialize a new NPM project. This is crucial as it sets up a package, JSON file that tracks all your project dependencies, scripts, and important metadata. To accomplish this, we'll run a simple command in our terminal. By executing this command, you're automatically generating a package, JSON file with default settings, which will allow you to easily manage the required libraries and tools for your TypeScript application. This setup will help keep your project organized and ensure that anyone else working on the project can easily install the same dependencies we are using. Once this step is complete, your project is ready to proceed with installing TypeScript and configuring it correctly, which is essential for writing and compiling TypeScript code effectively. Remember, this foundational setup is part of ensuring a smooth and consistent development experience as you build your application. Next, we will install TypeScript as a development dependency to manage the types in our project effectively. This is accomplished by using the npm command that adds TypeScript to our project's dependencies without including it in the final production code. Once installed, we need to initialize the TypeScript configuration. This is done easily with the npx command, which generates a new TypeScript configuration file named tsconfig.json in our project directory. Now let's take a look at the default settings within tsconfig.json. The compiler options key contains important configuration options. The target defines the JavaScript version we want TypeScript to compile to. We're opting for ES 2016 for modern JavaScript features. The module setting is configured as commons, appropriate for Node.js applications. The Ease Module Interrupt option allows for default imports from modules lacking a default export, enhancing module compatibility. Additionally, we enable strict mode for robust type checking, which is a good practice to ensure type safety throughout our code. With these configurations set, we have the foundation for a solid TypeScript project that optimizes code quality and maintainability. Now that we have our project structure set up, let's proceed to create the source and distribution directories. First, we use the mkdir-srcdist command, which stands for make directory. This command helps us establish a clear separation between our source files, which contain the raw TypeScript code, and the compiled output in the dist directory. Organizing files in this manner is a best practice that promotes maintainability and clarity in larger projects. Next, we'll write a simple TypeScript program in the index.ts file. For this, we can add the line console log, hello, TypeScript. This code uses the console log function to output a message to the console, demonstrating the basic functionality of our TypeScript setup. It's a great way to confirm that everything is working correctly before diving into more complex logic. Finally, to compile our TypeScript code to JavaScript, we execute the command npx-tsc. This command invokes the TypeScript compiler, which reads the index.ts file and produces a corresponding index.js file in the dist directory. This process transforms our TypeScript code, including its type annotations, into standard JavaScript that can run in any JavaScript environment. Now let's take a look at how to run our compiled TypeScript code using Node.js. To execute the JavaScript output that was generated from our TypeScript files, we will use the Node.js runtime. From the terminal, you can run the command node dist/index.js, which points to the compiled JavaScript file located in the dist folder. If everything is set up correctly, you should see the message, "Hello, TypeScript." Output in your console, confirming that your TypeScript project is configured and functioning properly. Next, we will write a clear project structure to accommodate both client and server code. A well-organized project will include separate directories for client and server configurations, each containing their own tsconfig JSON files. This allows you to tailor the TypeScript compilation options specifically for the environment in which the code will run. The client tsconfig JSON might include libraries for DOM manipulation, while the server configuration will specify node-related types. Finally, if you're sharing types or interfaces between client and server, it's useful to create a shared directory that can be referenced in both configurations to promote code reusability. Now let's take a look at the shared configuration for TypeScript by creating a tsconfig JSON file in the shared directory. This configuration is designed to facilitate the sharing of types and interfaces between both the client and server sides of your application. In this tsconfig JSON, we specify that composite builds are enabled by setting composite to true. This allows TypeScript to manage dependencies more effectively and ensures that the compilation of shared components can occur without issues. We also define the out_dia as dist_shared, indicating where the compiled JavaScript files and declaration files will be stored. This keeps your shared code organized and separate from the client and server outputs. Moreover, by setting declaration to true, we instruct TypeScript to generate declaration files alongside the compiled JavaScript output. This is crucial for enabling type safety and allowing both the client and server to use the shared types seamlessly. Finally, we enforce strict type checking by keeping the strict option enabled, promoting better coding practices, and enhancing the overall quality of the shared code. This setup ensures that your project can maintain clarity and efficiency, especially as it scales. As you continue your journey with TypeScript, remember that the type system is there to help you catch errors early. It encourages good practices and yields better code quality throughout your projects. Don't hesitate to explore features like interfaces, generics, and advanced types, as these will enhance your development and utilize TypeScript to its fullest potential. Whenever you're unsure about configurations or need to adjust settings for your project, don't forget that the TypeScript documentation is an excellent resource, guiding you through the nuances of setting up various environments and configurations effectively. As we wrap up this session on project setup fundamentals, it's crucial to remember the path ahead. The flexibility TypeScript offers, combined with the robustness of your configurations, empowers you to build scalable applications efficiently. Now you are all set to dive deeper into TypeScript development, armed with a solid project setup. Thus far, we have discussed setting up a TypeScript project, from installing Node.js to configuring TypeScript for both client and server code bases. As we move forward, we will delve into specific features of TypeScript, allowing you to write high-quality, maintainable. You want to use TypeScript for a certain framework or platform, but don't know where to start with your configuration. No worries, today we'll dive into advanced configuration for TypeScript projects, allowing you to tailor your setup for specific needs effectively. So far, we learned how to set up a TypeScript project, including installing Node.js, initializing an npm project, and configuring TypeScript for both client and server applications. We created a basic project structure with separate directories for client, server, and shared types, along with individual TypeScript configurations for each. Additionally, we wrote and compiled a simple TypeScript code, demonstrating proper setup for running applications. Now, we will explore specific features of TypeScript to enhance our coding practices further. Let's start by understanding how TypeScript can be configured for various frameworks. Frameworks like React, Angular, and Node.js each have their own peculiarities and best practices that can affect how you configure TypeScript within your projects. The core of this lies in the tsconfig JSON file, where you can adjust various settings to optimize TypeScript's behavior for your needs. This file is the heartbeat of your TypeScript setup, dictating how the compiler works and the types of features you can leverage. Now let's take a look at a typical tsconfig JSON setup for a React application. This configuration file is crucial as it dictates how TypeScript behaves in your project. The Compile Options section specifies several key settings. For instance, setting target ES6 ensures your TypeScript code is compiled into ES6 JavaScript, which brings modern features while maintaining compatibility with most environments. The Module Commons option indicates that the compiled code will use common JS module syntax, commonly required in Node.js environments. A significant feature is the JSX, React JSX setting, which enables proper handling of JSX syntax. This allows you to write React components seamlessly, facilitating effective UI development. To enhance code quality, the strict true option enforces strict type checking. The base URL, src, configuration aids in simplifying module imports, letting you write cleaner code without deep relative paths. Other options like FOSS-consistent casing in file names ensure file names are consistently cased, preventing potential errors on case-sensitive file systems. Finally, including skiplib check, true reduces compilation time by skipping type checks on all declaration files, streamlining your workflow. Now let's see how we can create a custom declaration file for a JavaScript library that lacks its own TypeScript definitions. In our case, we're going to define types for a hypothetical library called AwesomeLib. Begin by declaring a module for AwesomeLib using the declare module syntax. This statement informs TypeScript that we are augmenting the type information for this library. Inside the module, we will define an exported function named AwesomeFunction, which takes a single parameter of type string and returns a number. This establishes a clear contract regarding how the function should be used and the expected types for its input and output. Additionally, we have an exported constant, awesomeVar, defined as a string. By providing these type definitions, we enable TypeScript to perform type checking when this library is used in our project. This not only improves code safety by reducing potential runtime errors, but also enhances the overall development experience, as TypeScript can now offer better tooling support, such as autocomplete and IntelliSense, when working with AwesomeLib. Now let's take a look at an example of a TypeScript configuration file tailored for a Node.js application. This configuration, specified in the tsconfig JSON file, begins with the compiler options section, where we set the target to ES 2018 to leverage modern JavaScript features. The module option is set to commons, adhering to Node.js module standards, while the out dia specifies that compiled files will be directed to the dist folder, which helps maintain a clean project structure. Continuing, we set root dia to src, indicating the source file's location. The strict flag is enabled to enforce strict type checking, enhancing code safety. By using EaseModuleInterop and skiplibcheck, we ensure compatibility with common JavaScript libraries while skipping type checks for declaration files respectively. Additionally, the experimental decorators and emit decorator metadata options are specified, which are crucial when working with frameworks like Nest.js that utilize decorators heavily. These settings allow for the attachment of metadata to classes and methods, streamlining dependency injection and configuration. Finally, the include and exclude arrays help specify which files to compile and which to ignore, refining the compilation process. Overall, this configuration offers a solid foundation for any Node.js backend project using TypeScript. Next, we will write the following configuration in the tsconfig JSON file to define how TypeScript resolves modules in our project. By setting the module resolution option to Node, we instruct TypeScript to adopt the same resolution strategy used by Node.js. This is particularly useful when working with packages installed via npm, as it allows TypeScript to automatically locate modules within the Node modules directory. With this configuration, you will find that the process of importing libraries and modules becomes more intuitive and conforms to the ecosystem's conventions. For example, if you're using a library like Express or React, TypeScript will seamlessly locate and integrate these modules without any additional hassle. This adjustment enhances compatibility with existing JavaScript libraries, ensuring smooth integration within your TypeScript code. Adopting this module resolution strategy can ultimately simplify the development experience, making your codebase cleaner and easier to maintain as your application grows. Now let's take a look at how we can streamline our project directory structure by defining path mappings in our tsconfig JSON. This configuration allows us to set a base URL, which serves as the starting point for module resolution, simplifying imports throughout our project. In this specific example, we set the base URL to the current directory, represented by a dot. Next, we define a paths property, mapping the alias at components to src/components/**. This means that whenever we refer to a component using the @components prefix in our imports, TypeScript knows to look in the src/components directory. This approach helps us avoid complicated relative paths that can quickly become unwieldy and confusing, especially in larger projects with deeper folder structures. For instance, instead of writing out a lengthy relative path to import a component, we can simply refer to it using the cleaner alias. By adopting this structure, we improve the readability and maintainability of our code, making it easier to scale our applications without getting lost in import statements. Next, we will write configurations that allow us to manage different TypeScript settings for various environments effectively. In a typical project, you can create nuanced configurations for development and production by setting up separate tsconfig JSON files such as tsconfig dev.json and tsconfig prod.json. Now let's implement the development configuration. In tsconfig dev.json, we enable strict type checking by setting strict true. This ensures that TypeScript will catch potential errors early during development. Additionally, we include source-map true, which helps debug the original TypeScript code instead of the compiled JavaScript, enhancing the development process. The compilation output is organized in the dist directory without generating any intermediary files by setting no-emit false. On the other hand, for production, we will create tsconfig prod.json. Here we opt not to use strict checks by setting strict false, as this might streamline the application's performance for users. We also disable source maps with source-map false, which helps in reducing the bundle size before deployment while still organizing the output in the dist folder. To facilitate easy switching between these configurations, we define scripts in our package, JSON. With commands like build dev and build prod, you can quickly compile the project depending on your working environment, making the workflow smoother and more efficient. As you can see, the versatility of TypeScript and its configurations allows you to adapt to various projects and frameworks neatly. It provides you the tools to enhance the development experience through proper type safety, ease of debugging, and improved code quality. The configuration options available set the stage for greater scalability and maintainability as you progressively build your applications. At this point, you should now feel more empowered to tackle advanced TypeScript configurations, whether you are working on a React front-end or a Node.js backend. With every configuration option we've discussed, understand that it's about making your coding life easier and your applications more reliable. Remember, every choice you make in your tsconfig JSON plays a vital role in shaping the behavior of TypeScript in your project. In conclusion, becoming familiar with advanced TypeScript configuration gives you a significant edge in writing better applications. Explore each option we discussed and see what resonates with your projects. Each setting helps you build a foundation that paves the way for organization, clarity, and type safety in your growing code base. The more you configure, the more you enhance your coding journey with TypeScript. Happy coding. In this final section, we will do a project challenge to apply what we have learned so far. The goal of this project is to develop a simple TypeScript application that implements a RESTful API for managing user data through basic CRUD operations. You will set up a new TypeScript project, define interfaces to model your data structures, and implement functionalities to create, read, update, and delete user information. As you tackle this challenge, you will utilize TypeScript's powerful type system, including interfaces, generics, and conditional types, to enhance code quality and maintainability. Additionally, you'll establish a basic API using a web server library like Express and ensure robust error handling and type safety throughout your application. To test your work, write unit tests to confirm the functionality and integrity of your CRUD operations. You can find the final project in the GitHub repository linked in the description, so get ready to dive in and showcase your skills.